So with this brief introduction, let me conclude now. I wish all the best to all the speakers and participants for this symposium. Thank you.
May I now invite Professor Prakash Patil sir to share his view about the theme of the symposium.
Okay, first, thank you very much for inviting me here, and thank you for all the hospitality I received so far. Then again, respected and honorable Vice Chancellor Professor Shirke, two other invited speakers, head of the department, and Somnath, and you all friend. I'm supposed to speak on the theme, but I just checked the time. It's 10 minutes late. My time is over, but I'll try to finish quickly. But before theme, let me just quickly mention the timing of this symposium. Timing is so perfect, they made it possible for me to attend this one. So thank you very much. Now about the theme. Yes, actually, I'll go straight to the point about the non-parametric methods. Well, there are two kinds of non-parametric methods. One is called rank-based, another is called smoothing methods. Since I'm not expert in rank-based, even though I did bit of pieces of work here and there, I will leave that discussion to Professor Madhurao. So I'll just talk about a smoothing method. Smoothing method, why this is a good time to have a symposium? Well, for the following reason. Actually, smoothing method started by mid-50s to mid-60s, and up to mid-70s or early 80s, only thing we knew about that one, it's an estimation technique. It wasn't as an inference procedure could stand on its own. But next 10-20 years, people started developing tests based on that one, confidence interval based on that one, in all areas. Density estimation, regression estimation, intensity estimation, all sorts of functions. And now we have come to kind of a point where this smoothing methods itself could stand on its own as an inferential procedure. The main buzzword behind that one, as Professor Mahadik mentioned, that parametric procedure is wonderful, but you put a lot of restriction before you do analysis, is exactly opposite. The basic principle is let data speak for itself. That's what the philosophy behind the smoothing method is. Now, having developed all those things, why is the right time to have this conference right now? Well, for the following thing. We have seen that we have changed in terms of the kind of data we are getting. We are getting data with the high velocity, high volume, and high dimensions. So the big data is coming up. And how to deal with that one. Another thing you must have noticed, nowadays, rather than inference, there is an algorithmic way of doing inference is more common, right? And for those things, there is nothing like, by and large, what we have is unknown truth, and we try to get at it. Density function, the regression function, or whatever it is, that is what we have to get at. But in this big data world, there is nothing like a fixed truth. What they have is they'll have some whole data divided to half, train data, the data on which you train, and then other data used for testing, whatever that kind of thing. That means there is nothing of truth. So in this case, of course, parametric is pretty much out of question, but smoothing methods still have. Meaning the way to look at the smoothing method now has to change. Meaning rather than doing the following thing that we did, like, okay, we are estimating a density function fx, and how best to estimate it is, well, unknown f, estimated f, take a difference, take some error criteria, maybe L2 error, and try to see which estimator will minimize that one. But now there is no true f. But still, these procedures are useful to find, to solve the problems that we face. Meaning the problem that we face is, again, this pattern recognition, how what data is telling you. And for all those things, there are numerous smoothing methods are available or tools are available. And so the focus should be on how those should be used, and that is why this theme of the timing, and this theme is very useful at this point in time to talk about the smoothing methods. Okay. I guess I can say a bit more, but as I promised you, I won't be taking more than 3 minutes as we are late. So maybe I'll stop here. I would have liked to say something more about slightly outside the topic, about the university and about, what I saw here, like a homegrown talent and what we need to do, but maybe some later time, or maybe I'll share with the head of the department later on. Thank you very much for giving me opportunity to come here and talk to you. Thank you.
Thank you so much, sir. Now I invite Professor K.S. Madhavrao to share his view.
So good morning to everybody. It gives me a great pleasure to be here amongst all of you today. Let me first congratulate the University of Shivaji University for their useful existence of 60 years. And I hope my wishes will be conveyed through the Vice Chancellor to all those people who have brought the Shivaji University to the level that it is known all over the country. Okay. I am very sure under the dynamic leadership of Professor Shirke, so this Diamond Jubilee year is going to witness several more such useful academic activities, not only in the discipline of statistics, but also in all the disciplines that the university is propagating and professing. Okay. Well, I am supposed to share my thoughts on the theme of the symposium for the next 3 minutes. So this is a community of teachers and students, and if I breach this time limit of 3 minutes, and please be indulgent and be patient. Okay. Yeah. So in fact, this is the first conference after the post-COVID that I am attending, and I am more delighted to be one of the participants for the simple reason that the theme of the conference is something close to my heart and an area which I have always worked all through during my 50 years of teaching experience. Okay. Well, non-parametric inference, as we all know, always rides piggyback on parametric inference. Okay. If you go through the vast literature that is available in journals, as well as very elaborately, effectively and succinctly carried in maybe dozens of books on non-parametric inference, you will see that for every parametric concept there is a non-parametric conquest evolved over the years. Okay. But if you look at the recent trends, so maybe because of the advent of machine learning, the data science and its other different branches and artificial intelligence, so there are indications that non-parametric can be a real field of research without really looking through the window of parametric inference. Okay. So maybe in the afternoon session I will give some examples where this thought of non-parametric inference thought has emerged independently, and there are no parallels to these concepts in parametric inference. Okay. Having said that, it is very appropriate that we are having a symposium on non-parametric inference. So this non-parametric inference has served the researchers, not necessarily in the discipline of statistics, but most of the parametric, most of the practitioners. Okay. If you look at the wide variety of the articles published all over the world in the last 75 years, you will see the more practitioners have used non-parametric techniques rather than the parametric techniques. Okay? So be it varied disciplines like medical statistics or maybe industry or the social scientists. So scientists have always been more comfortable in using non-parametric methods rather than the parametric method, as my earlier speakers have pointed out the limitations that are normally carried forward in parametric inference. Okay? So I am very happy that the Department of Statistics has thought of organizing an international symposium on this very important theme, and I am very sure during the day we'll have more deliberations and critique on this particular dimension of statistics. Okay? So with this brief my own overview of the topic, I will hand over the mic to the organizers.
Now let me invite Professor Ramanathan sir to share his view.
Good morning, everyone. Respected Honorable Vice Chancellor, Professor Sirke, Professor Patil, Professor Madhav Rao, Professor Mahadik, Dr. Pawar, and all the teachers and students. I'm very happy to be here. Of course, I used to come to any occasion that I get to come to Kolhapur because I love this place. So whether it is a RR committee meeting, whether it is a board of studies, whether it is just a talk in the department, I make it a point that I come here, talk with the people. So that kind of attachment is there. So, and they have been sort of, entertaining me for last several years. So very thankful to the department for inviting me. And regarding the theme, it was very interesting. Like all of you, when you do masters, you don't know much about the statistics, and whatever is being taught, we just study. The same thing with me also. And then I came to Pune to do PhD. So I was talking to, we have a wonderful teacher, Dr. Dharmadhigari. So Dharmadhigari is very enthusiastic and do a lot of industrial consultancy and things like that. Well, I never had any experience of that. I'm typical, XYZ kind of person. So one day Dharmadhigari was saying, Ramanathan, let's sit for some time. So then he had some data. Those days Chetak was hot, scooter. It was very difficult to get Chetak scooter. You have to, booking period is something like 6 months or more than that. So I got some data from this Bajaj company. And then this industry people are saying that this data is normal. But I don't see this is normal. I did all kinds of tests, whatever test that is available in the literature, but this doesn't show normal. Then I told, I don't have much of an idea. Then he, okay, let's look into that. Then he told, see, those Bajaj people are trying to find what is called this capability index. Very simple idea. What is that specification? USL minus LSL divided by 6 sigma. So immediately I asked Dharmadhigari, what does this 6 sigma stand for? I really don't understand. Because we have learned something like plus or minus 3 sigma. Is that the thing? Because I never had this in quality control as a course. So Dharmadhigari, no, 6 sigma is related to normal. Then I think that is the point, because there is possibility of non-normality. So why don't we modify this? So we modified it and published. That's a different thing. What I'm trying to say that in the process, when we sent this paper to a very top journal in statistics, that's the thing which I want to share you, how the things have got changed. We thought that we have done some wonderful thing. We sent it to a top journal in that area. And you know what was the response? They said that, no, this is nonsense, absolutely rubbish. Because an industrial process cannot be non-normal. If it is non-normal, there is a causal reason for that, and you should remove that reason, and then it will become normal. I told, is that the case? What I want to say that at that point of time, people were not even willing to buy the idea of non-normality, and then of course, there are, as Dr. Madhav said, parametric things changing to non-parametric, but in specific areas where there is a possibility of non-normality was not very much acceptable, because they think that there is an assignable cause for that, and you remove that cause, everything will be normal. In fact, this is what the feedback I got from a consultant who solved about 50-60 problems of industry. But being statistician, we never, we don't want to believe it. And that's where, I started thinking like there is always a possibility of non-normal things. And that leads to some interest. And as you know, when you start working, you generally work with what your professor does. So unfortunately, I want to work with a professor. Professor left to America. So I couldn't work on that. So the other professor whom I got, he said, I don't have any idea of this non-parametrics. I am interested in stochastic process. So I told, yeah, stochastic process, something I know, but I don't have much of idea, because I did some kind of neither non-parametric nor semi-parametric. Perhaps you may be knowing what is called U statistics, generalization of mean. See, mean is a simple average. You can generalize in by considering the combinations and then take the, so that many statistics can be represented like that, so that central limit theorem, other things are available. So this professor told me that maybe we can have a marriage of both, like a stochastic process and non-parametric. That's how I landed up a little bit of non-parametric things. Well, over the period of time, my interest also, depending on where you work, where you do, got changed. But I made sure that at least something that I do relating to the non-parametric also. So that's the kind of interest. And I think in today's era, as every speaker was saying, it has got a lot of importance, especially when you have data which, especially time series data, which are kind of things that you apply, like neural networks, the so-called AIN neural networks, or LSTM. So all these things, basically what is that you are trying to go away from the normal things or linear things, and then see that what is the consequence of that, how you can connect the things. So the entire neural network is basically in terms of the kind of nonlinear functions, and how you can actually forecast or predict, as Professor Madhav was talking about. So this is kind of my take on this theme. So I think this is a correct theme and apt timing. Well, we are fortunate to have Professor Patil around, so you can listen. He has done wonderful work in smoothing with pioneers like Peter Hall and J.S. Maron and people like that. So you can also hear, and I would consider this as a good opportunity for you to interact with him. So I'm sure that all of you will have a lot of things to take away during the end of, by the end of today. All the very best. Thank you.
Now I invite Professor D.T. Shirke sir, Honorable Vice Chancellor, to pass the presidential remarks.
Good morning to all of you. The chief guest of inaugural function of One-day International Symposium on Nonparametric Statistical Methods, the authority in the nonparametric methods, nonparametric procedures, Professor Prakash Patil from US, Mississippi State University, Professor K.S. Madhav from Narsingh Munji Institute of Management Science, deemed to be University, Mumbai, Professor Ramnathan, head of the Department of Savitribai Phule, Pune University, and again, all the three eminent speakers are having a wide international exposure, and in true sense, this symposium is international. On the dais, we also have the captain of Department of Statistics, HOD, Professor S.P. Mahadik, and the convener of this particular symposium, Dr. S.D. Pawar. one of the senior professors of Department of Statistics, Professor Kulkarni. We also have Director of School of Computational Sciences, Professor V.B. Gute from Kolhapur University, former Chief Statistician of MSRTC and the present Adjunct Professor Sanjay Ji Ganjwe. We have many names, but my 3 minutes would be over in taking these names. But all the teachers, research scholars, and student friends. First of all, let me congratulate Professor Mahadik and the Department of Statistics for having organized this international symposium on non-parametric methods as shared by all the 3 speakers. It is really a good time to organize such an event and a good theme also to organize such an event. But sometimes I feel that whenever such conferences are organized, students are invited to participate in the conference. And students are always in a doubt that what is their role in the conference. This being a small conference, they were not having a lot of burden of logistic help or something like that. But they would realize this importance when they leave the department. They had attended such and such a conference, such and such talk was given, and they will try to recall, give stress to their memory that this was discussed. Fortunately, the topic or the theme of the conference is very well known to the students also. I would just try to make the gap between a very heavy terms in non-parametric methods and the students by just reciting a very simple example which will connect you, all of you, with the non-parametric methods. I would say that if these eminent speakers permit me, they can raise the query, they can raise objection also because they are authority in that. Before you come to know the concept of non-parametric, you started doing that. I don't know when you started doing that. You started doing data analysis, and the first thing what you did is you got the histogram. And you try to make it smooth by picking up the top points, midpoints, and then had a smooth curve. And that is all. You got a non-parametric estimator of density function, and you have done it quite a long, maybe in the UG level or maybe in the 11th standard or test standard. You may say that, then what is great in non-parametric? Then I would advise you to open in any of the journals that Dr. Pawar spelled out. May it be Annals of Statistics, may it be Journal of American Statistical Association, may it be a multivariate analysis, and try to understand a para of that particular article. And that will motivate you, at least motivate you to know more about that particular thing. And that will also tell you that what kind of mathematics is required to investigate the properties of even what you did as a smooth curve. It is a really beginning. And end, I think there is no end, and we'll have to keep on doing, and so on and so forth. Very interestingly, it is not that abruptly they chose a topic and organized non-parametric as a theme of this particular conference. To the best of my knowledge, we are missing Professor R.N. Rattiali, who happens to be again very close to the topic that Professor Patil is going to talk about, the symmetry, testing symmetry, and so on and so forth. So Professor R.N. Rattiali and if I am correct, Professor H.V. Kulkarni, they have a joint paper in JASA long back in 2002 or 2000 maybe 20 years before, published in JASA. So this perhaps could be the first paper in the non-parametric methods which was published by the department, according to my knowledge, in a very top journal. Followed to that, Professor Mahadik presently is dealing with control charts based on non-parametric methods. As I told you, Professor R.N. Rettiari has published several papers besides the paper that I quoted. Dr. Somnath Pawar and D.T. Shirke and his group, they have quite a bit papers on data depth related to that, and of course the non-parametric control chart. Some of the audience, they are also having very typical papers based on non-parametric. But these days, since the last maybe 5 years, I am thinking that statistics is becoming a rare event for me as far as this kind of functions and occasions are concerned. Though formally I am not involved in putting theta, beta, alpha on paper, every day I have been using statistics a lot, and that too I have been using only non-parametrics, because there is nothing like a distribution I can fit to any situation. So I will have to first assume that there is no distribution, you have to work with that. And my non-parametric starts daily. It could be a person whose behavior is to be modeled. There is no normal distribution. So everything, many times it is a non-normal. I would not say abnormal, but it is a non-normal. Definitely it's skewed. Maybe sometimes left skewed or right skewed and so on and so forth. I do work with the counts, I do work with the ranks, and so and so. And I always insist in making the smooth administration, and that is how the smoothing is always a continuous process in the decision making. Mind it, I learned that because there are more number of students, so I have to basically address the students. Here also I am using statistics. I learned that many of the students, they are not much interested in the research. And they are after what is called as, of course, the career is important, job is important, bread and butter is important. It is important from everyone. But it is not that earlier people were not having this kind of issues and they entered into research. It was not so. So therefore my appeal to all of you, advice to all of you, that at least 10% of you should be very serious in entering in this particular career, research as a career. And for that, what you need is a lot of patience. Professor Prasad used to say that statistics is to be learned and mastered. You require 3 P's. You require a pen, you require a paper, you require patience, and nowadays, of course, the PC also, the 4th P has come. And PCs, I don't think that you have any issue as far as Department of Statistics is concerned. Rather, PCs might be having issues that they are waiting for you to, okay, all the while they are ideal. So all the 4 P's are with you, and this university has got wonderful resources. You may not be knowing, but let me tell you openly, we are spending 2.5 crores every year on the research journals. 2.5 crores. And we are making all these journals available to everyone on the campus as well as outside campus. It is public money. And who should use it? It is for you. It is not only a very handful number of research scholars, but you student also should know that. It could be the American Statisticians Teachers Corner, okay? Many times I think your HOD and your colleagues, his colleagues might be insisting to take a topic from a research journal for seminar, for project, and so on and so forth. Make a point to open these journals and try to read some of the papers in these journals. And that is how that will at least motivate you to enter in this particular research field. The field is very interesting, and sky is the limit. If you really want to do something good, better or best in statistics, don't run after only picking a job. You can postpone some time and spend some time in this particular area. I also advise you, it is not that always you have to be the best in mathematics immediately the next day. Yes, it is required, very much required. You can't get away from that. But you should have a feeling of where it is to be used and what exactly is to be used if you really want to maintain the quality of what you are seeing and acceptability of the same in the market. So mathematics doesn't have any option. You will have to do that. And if you really want to do the best in statistics, you have to be the best in mathematics as well. And that you will realize when you listen to these 3 authorities in non-parametric methods. I think President doesn't have a time limit, though it is mentioned on the, but I will have to maintain some protocol and see that the entire day schedule goes very smoothly. My best wishes to all of you, particularly to the students, research scholars, and to the faculty of the department. I am really grateful to Professor Prakash Patil, who is on sabbatic leave visiting Savitribai Phule Pune University, who made a point to visit Shivaji University on the request of Professor Mahadik and his colleagues. Otherwise, it's very hard to get such a personality and inviting and making it to happen as far as our university is concerned, because of lot many issues. The first is connectivity and so on and so forth. Rather, my request is that Professor Patil, whenever he happens to visit Pune, if he lets us know that he is visiting Pune, and on behalf of Department of Statistics and on the behalf of University, we have a standing invitation to Professor Patil to visit Shivaji University in future too. And the same is the case for Professor K.S. Madhavara, and I think Professor Ramnathra doesn't need any formal standing invitation, because he is at, I think whenever you call, yes, he will make a point to visit. All of three, in fact, Professor Patil has not seen our campus. If he's, if you have a look at least, if he has a look at least for an hour, he may think that tomorrow should he leave early morning or delay his departure. Students, another advice to all of you is that we have the best place to study, the best I'm saying, and this you realize when you leave the campus. So 2 years, 365 multiplied by 2 days, multiplied by 24 hours, multiplied by ... Try to use optimally, effectively on campus. If you do that, I think you have a very bright career in statistics and outside statistics also. My best wishes to all the students, and of course to research scholars and my teacher friends. And I'm sure that this is going to be a grand success as far as academic event is concerned. Thank you for inviting me. Thank you, and have a great time.
Thank you so much, sir, for the presidential remark. Now we will end this inaugural function with the vote of thanks. Now I invite Sukumar Rajguru, sir, to propose vote of thanks of this inaugural function.
Honorable dignitaries on the dais and of the dais, fellow participants, research students and students of M.Sc. Statistics and Applied Statistics and Informatics. I feel honored and privileged to get an opportunity to propose a vote of thanks on this special occasion. First of all, on the behalf of Department of Statistics, I would like to thank the President of this inaugural function, Honorable Vice Chancellor, Shivaji University, Kolhapur, Professor D.T. Shirke, for accepting our invitation to preside over this function and sharing his views. You are a part of our statistics fraternity of Shivaji University, Kolhapur. Your guidance and support always valuable for us. I would like to thank today's distinguished guests, Professor Prakash Patil, Professor K.S. Madhavrao, Professor T.V. Ramnathan, for accepting our invitation for delivering lectures in symposium and expressing their views about today's event. I would like to thank Head of the Department, Professor S.B. Mahadik, for taking initiative to organize this international symposium and guiding us for organizing this event. Also, I would like to thank convener Dr. S.D. Pawar, who has taken a lot of efforts for organizing this event. I extend thanks to all organizing committee members. Also, I like to thank all the participant research scholars, students for participating in this symposium. Also, I extend my sincere thanks to all other teaching and administrative staff of the university for their presence for this function. Once again, thank you to all. Thank you very much.
So with the permission of chair, I declare the inaugural function is over. We immediately start our first invited session. I request dignitaries. We'll start first invited session by Prakash Patil sir, and I request Ramanathan sir to chair the session.
Good morning, everyone. So we are going to start our first technical session. We have Professor Prakash Patil. He is going to talk on non-parametric curve estimation, kernel and wavelet-based non-parametric smoothing methods, robust statistical methods. Of course, he is also maybe touching upon symmetry of a continuous probability density function as well. So the floor is yours, please.
No, it's okay. Which one is this one? This is open. This one. Okay, that's the idea. Is that okay? Is that okay?
Yes. We will make it full screen.
Full screen, yeah.
Alt F5. Control.
Let him do it. Yeah. Right, yeah, I can do it on the computer as well.
I think.
All right, thank you. Okay. Now, again, thanks for having me here. But let me directly go into the talk. We're running behind the schedule. First thing, this work is not only my own. I have several collaborators as I started sometime around 2010 working on that one. Those names will come as I go along talking about this one. I have a habit of, well, not habit. Generally, I used to give a talks on chalk and talk on the blackboard. And that's why I could, depending on the day, the way the thought process will go, that is how I used to talk. Now we started having these slides, but still I end up doing the same thing. Therefore, I might talk something, the slide will come later, or maybe I'll talk something, the slide will be behind. So that kind of coordination I could never manage. So today I'm going to have, well, from the last seminar I gave, I started doing something different. That is, I'll open the slide, I'll talk about the slide for a few minutes, and in there, next slide, talk about it, and go ahead. Hopefully, by end of it, the story will be complete. So anyway, today I'm going to, if this is the title, it says Revisiting, Measuring and Testing Asymmetry and Symmetry of a Continuous Priority Distribution. So it's a revisit because there's already a lot of work on measuring asymmetry or testing symmetry. So let's see why all this thing happens through following way. So, okay, as I said, I'm going to talk each slide and talk about it. So first, I'll give motivation, why I'm doing what I'm doing. Then I'll go and talk about symmetry and asymmetry of a univariate probability density function, a very simple concept. Then what are the measures of asymmetry, testing for symmetry. Then I'll go to bivariate setup. Well, one can think about multivariate, but I'm going to restrict my attention to bivariate for very special reason. And then I will also do the similar thing what I did for the univariate, that is, can I measure a bivariate asymmetry, can I test bivariate symmetry. All right. So first, motivation. I think there are 3 points I mentioned here. The first is a paper. I have no idea. I never went to the library to get that paper, but for some reason somebody came and that paper stayed on my desk. Maybe some guy visiting Birmingham, giving a talk, and that paper was stayed there. And okay, and somehow I got opened that one and I started reading it. What it had was something of following type. They were trying to compare the economies of different European nations, because they wanted to have one currency, and the paper was written before that, and the idea was after few years of time all economies should look similar, and therefore they had a data on 8 or 9 different European countries, and their income distribution was mentioned. And there they're comparing how all these 8, 9 different economic distribution compare, how similar they are. And there are measures of alpha major, beta major, there are kurtosis, but they did not have, in that comparison, a symmetry. And I thought maybe they should also look at the symmetry, but then I realized maybe they did not know how to measure asymmetry, or there are measures but they may not be happy, and one needs a measure of asymmetry to measure that asymmetry, and that might be the reason they may not have used it, but I thought I should think about it. That is first time the thought came to my mind about measuring asymmetry. Secondly, after some time, I noticed that in finance and risk management, they model dependent structure between 2 random variables, by and large bivariate random variables. Those who work on the copula, they might have known that that the important thing there is they are worrying about the symmetry in two random variables. Symmetry in a slightly different symmetry, or other buzzword for that one is exchangeability. So that is the kind of symmetry in a bivariate setup they are interested in. And then very soon after that, I have a friend working in SAS, and he came and he said, no, Prakash, this is interesting because this symmetry thing, we have those symmetry, there is no good measure, and when you write data algorithm, we don't go and do test and all those things. For example, think about correlation coefficient between two variables. They simply, the way the algorithm works is compute correlation coefficient, or if it is above 0.5, below 0.5, strong correlation, that's all they do. So if you could give me a measure of asymmetry, we say that, oh, it is kind of symmetric, kind of not symmetric, some quantity on a scale, and that will be fine. And that is why I started working in the symmetry. Okay, so that slide explained. Here is the definition. Have a look at it, and you will find that there is nothing strange. You already know it. Probably very first course in probability or distribution, you know what the symmetry stands for. That is the first one. If you think about expressed in terms of a capital F, or those who statistics don't know that capital F is cumulative distribution function. What it says is that the probability below theta minus x is same thing as probability theta plus x for every x, and that's symmetry. Or if you think about the density function, the value of the density function below x units of theta and above x units of theta, it's same, and that's a symmetry. Okay. All right. So I think here I'm saying measures of asymmetry. So if I started thinking, well, I want to think about measuring asymmetry, but what kind of measures already exist? And I found there is actually, I did not mention that was a very, very old paper in early 60s or 70s written by Doxam and Bickel about all these properties of the curve, but that is a bit descriptive. And then I found McGilvrin's paper in 1986 in Annals, and he gave this measure. Now, well, you think about it, how it measures. First thing it does is chops out the two ends. Think about u between 0 and half. Take any u, take a small u, and look at the denominator. Denominator says that f inverse 1 minus u minus f inverse u. So you take a distribution, go left hand, go right hand, and then find that the difference, that distance, and look at the top, which is sum of those 2 points minus the median. If it is symmetric, of course the top would be 0, and the denominator is different, so that's a kind of a reasonably good measure. But think about it is you have to choose, and you are not covering whole range, right? And then after doing all those things, you find supremum, etc., etc. Note that alpha cannot be 0. That means it's not taking whole distribution into consideration. Okay. Then there are some other measures. This is by Booth, 1982. It also does a reasonable job. What it does is, well, take this f theta plus x minus 1 minus f of theta minus x, take a difference square, that will measure the asymmetries and integrate it over. And the same thing by Rothman, not much difference, only thing is a Lebesgue integral, that's a simple integral, and it gives the different measures. So, yeah, there is one more. This is by Lee Morris. I think that is probably like more, which says that, well, take a difference between your density function at theta plus x, theta minus x, find the absolute value. And if it is equal, of course that's 0, not a problem. If it is not, it gives the, it measures the asymmetry and integrate that one over. And clearly it is reasonably on a scale, that is 0 and maximum value is 2. So things are good. But as soon as you put an absolute value, doing any technique, any mathematics you want to work on it, it's quite difficult. estimation is difficult. Those are the issues it has, but otherwise it's a good measure. Okay, that's why I said at the bottom, not user friendly. Also problem with the estimation of it from a given sample. Okay, so after looking all these measures, what I still wanted, a number to reflect symmetry or asymmetry. Reflect meaning what? If I look at a density function, reflecting, for example, I have two density function, I should immediately, by looking at it, well, you can say that, oh, this is more symmetric, or this is slightly symmetric, and I should find corresponding numbers, and those numbers should say the same thing. Whatever my visible impression is, that should be there in those numerical values as well. That is what I was hoping to do. But just the definition, I realize it's not that helpful. Definition only tells me whether it's symmetric or not, but it's not helpful for me to come up with any measure to measure the asymmetry. So I started looking at two things, say y1, like the fx as a function of x, and I started looking at how as x moves, what happens to that. And then I realized, well, I can take two variables, y1 as actually a density function fx and y2 as capital Fx, because initially I said, oh, y2 is a constant, that is x-axis and the curve, x moves, what happens, but that variable is a 0, y variable is 0, constant. So there is not much I gain, meaning what I was intending at is the following thing. At the same point in time, I was trying to teach students how the covariance 0 does not imply independence. And then I realized when you have a density function, if that's the case, if I take x to constant, that covariance is always 0. But if I take cumulative distribution function, then when its density is symmetric, the covariance is 0. Right? But they are dependent. And that is, I thought, maybe my starting point. I started investigating actually the covariance between a density function and a cumulative distribution function. Well, and I can actually prove it. It's a very simple proof. Take your expected value of fx times capital Fx, and we can show that it is equal to product of their individual expected values, so covariance is 0. Right? So if student want to pay 1 extra minute, that's fine, you can go ahead. But the reason I wrote that one here is the following reason. That is, I know from top to bottom, it's one-way implications there, but can I go by reverse? I can say that no, I cannot go reversely, so it is not actually necessary and sufficient condition. That is, I can immediately notice that one. Okay? And that's why the proof is there. Any student want to say that it is necessary, why not necessary? He can try to go step by step and then realize the bottom state does not imply step before that one. Okay. So for a continuous fx to be symmetric, I need this condition, which is a necessary. And I thought, well, if this is true, then why not make a measure out of it, which could be on a scale 0 to 1 or minus 1 to 1 if you want, and find a correlation between fx and fx. And that may be able to do the job of measuring asymmetry. Okay. But I said, yeah, that is simply a necessary condition, and then it may not be good, so I should think about a necessary and sufficient condition to get a stronger measure, etc., etc. Okay, that is what the thinking behind it. So far so good. It's a very simple concept. Want to measure symmetry, so I just have a density function and a cumulative distribution function. Find the covariance, find the correlation. 0 symmetric, not 0 not symmetric. Right? Okay. Okay, so a necessary and sufficient condition. What I have done when I told you that covariance is 0 is following. That is, here I have integral of fx times capital Fx integrated over minus into plus infinity. Okay. Now I am doing slightly different. I am taking a p between half and 1 and I am simply finding expected value of fx multiplied by fx or defined over minus into xi. Okay. That is what I am doing. And that integration should be same as fx multiplied by again fx, but now it is defined on xi of 1 minus p to infinity, where xi p's, I should mention there, xi p's are actually simply your quantiles. You understand? Meaning, think about, no bad. So think about a curve going from minus infinity to some point xi p, right? And then other one is the 1 minus p to infinity. Of course, if they are same, if they are symmetric, those integrations should be same. That's a simple observation. There's nothing very, very involved there. But that actually leads to the, that actually leads to a necessary and sufficient condition. So this condition now I am going to exploit to find a necessary and sufficient condition which will be on the scale 0 to 1. For that one, I have now defined two different densities from a given density. The first density, as I said, go from minus infinity to quantile or the xi p and divide by p, it becomes density, right? And second one is exactly opposite of that. Good. Then for every p, I find the covariance between that fp and corresponding cumulative distribution function. I am saying for fp star and a corresponding cumulative distribution function. What should happen is that it's obvious that if you have these two covariances, they should add up to 0. What we have a necessary condition which was p equal to 1, and this is I am getting it for every p now. That's the difference between necessary and a necessary and sufficient condition. Does that make sense? All right. And if that's the case, well, then I'm through. I can find, rather than covariance, get the correlation between these 2 points, right, for every p. So I got the correlation, and then find there are different. Once you got the correlation coefficient of the rho p and rho p star, then there are different ways you can define the measure of symmetry. What I have done is I found the xi p plus xi p star absolute value, find the maximum of that one, or p half to 1, and multiply by minus 1 half. And I will later think about it why I did that one. And then I can convert that one. I don't want the density of fp and fp star, etc., etc. I want to define my measure in terms of the original density function, and I can do that one going back and expressing those fp star in terms of the original density, and that is why I have rho p and rho p star, and based on that one I got to measure eta. Okay. So meaning now this eta b is a necessary and a sufficient condition. If eta b is 0, your density is symmetric. If it is not 0, it is not symmetric. So I have two quantities we computed. One is eta b star and eta b. Eta b star based on a necessary condition. One particular case of that one is p equal to 1, and necessary and sufficient condition, which is eta b. But the question was, I know both are, when they are 0, I have a symmetry. If they are not 0, they are not symmetric. But I wanted to find out how good are these measures. Okay. I know that your eta b is also minus 1 to plus 1 because they are correlation coefficient.
eta b equal to 0 implies symmetry. That's very, very obvious to see. But does the calibration or the quantification of asymmetry provided by eta b matches with visual impression? And that is where my talk is not complete. Meaning, I did not include all the pictures, but I might show you a picture or something which is not on this slide or somewhere else, which I can show that picture to show that it does matches visual impression. Now, the question is, does our visual impression is consistent with the strict definition of symmetry? Okay, are we clear here now? I have wanted to measure the symmetry, sorry, wanted to quantify the asymmetry, wanted to measure between -1 to on a scale. I got all those things, and I want to see how good it is, but I don't have any curves to show you. But I think in the next slide, I'm going to do something else to, yeah, okay. For pictures, see this paper, there are lots of pictures, but some insight or analytical look to claim that the things that I just defined are sensible. And for that one, well, I'm not going to take both the things. I'll just take a simple measure which is based on the necessary condition, which is eta b star, and we know that when p equal to, as p tends to, sorry, eta b tends to eta b star at p tends to 1. Okay. So we'll just restrict to eta b star, and I would like to intuitively show you that the measure that I have, the quantification that I have, does make sense to measure asymmetry. Okay. For that one, yeah, I'm taking a pause because student might want to read the first bit. What I have is a density function, a simplest form of a density function, which is uniform almost, which is epsilon is 0 is uniform. It is our -1 to +1, and you can see the picture, which is like horizontal line at 0, line just below that one from the right hand side. That's a density function, right? So let's think about the most ideal measure of asymmetry, which is a common sense measure, which has nothing to do with what I earlier said. If such is a density function, the simplest form of density function, what you could think about is a probability. Well, let me first define the set. I define a set S epsilon. S epsilon is the set of points x where this density function theta minus x to theta plus x are not equal. So consider set of those points and find the probability of that set. And that will be my measure of asymmetry. I think it will not be that debatable that we can use that measure of symmetry, particularly for this simple form of density function. Okay. If you are convinced that that is the case, then note what happens here. It is clear that whenever your epsilon is 0, of course your density function should be symmetric, or eta 0 is 0, right? And whenever your epsilon is half, again it should be a symmetric density function, right? Because epsilon half, the bottom part is gone, half plus half 1, -1 to 0, 1, it is symmetric, right? About minus half. Good? But the important thing to note is following. That is, this function, that's eta epsilon, is continuous at 0, sorry, continuous at half, but is discontinuous at 0. Can you see that? As epsilon goes to 0, the value of eta epsilon keep going higher, higher and higher, and immediately it drops to 0. So that means it is discontinuous. Right? Let me see the next slide whether I do anything. Yes, I do explain that part. So if you want to go back and see the picture one more time, I'll look at it, and I'll come to this point again. That is discontinuous at 0 and continuous half. That is the important point. to intuitively show that whatever I defined earlier makes sense. Okay. Now, let epsilon be very small, then it is not that difficult to find where the median is, and the median is minus 2 epsilon divided by 1 over 2 epsilon, and note that at theta becomes close to 0 as epsilon tends to 0, and that's the median is exactly at 0, right? We know that is different. So, implication is that for a small epsilon, there is a very small interval around theta such that these values of theta minus x to theta plus x are same. That means this interval is this one, which shrinks as epsilon goes to 0. Or that is, as epsilon tends to 0, the set of values of x such that these are not equal consists of almost entire support, with the exception of increasingly small interval about the median. That is, f naught is symmetric, but epsilon is very asymmetric when epsilon is close to 0. That gives us the disconnect. As I described, epsilon goes to 0, function becomes more and more asymmetric, and exactly at that point it becomes symmetric. That's the disconnect. That's the only point I want to make. Okay. Now, we can, as I said, it is not a proof. Since I did not include a picture, I want to say analytically what I do makes sense. So it's just an intuitive feeling about what I do is right. So now let's go back and calculate our measure of asymmetry, that is eta b star, for that density function, and see whether it has that defining property that we said, that is that epsilon tends to 0, it should go to 0, but it should be discontinuous as 0, and epsilon goes to half, it should be again go to 0, but it should be continuous. Okay. That's the defining property. And yes, we can compute eta b star is the middle of the screen, and also at the same time, to show that this is better measure, I am considering other two measures, which is eta 2 and eta 3. I am sure you forgot what eta 2, eta 3 is, because I never stressed on that point. But if I had to, I will just go what eta 2 and eta 3 are quickly. Yes, this is boost. Oh, sorry, my bad. I thought I gave the number here. This is eta boost is eta 2 and eta rot is eta 3, and I calculate those as well. Okay, here you go. So I use the defining property to think about intuitively whether my measure does sense or not, and these are the values. Those calculations are not that troublesome. We can do those calculations, and as one would expect, the line is true, the middle line is true. That is, if I take eta b star at f naught, meaning epsilon is 0, or eta 2 at f naught, or eta 3 is f naught, or all those quantities at half, that is epsilon equal to half, it should be 0 because function is symmetric there. That all things satisfied. But your eta 2 and eta 3 are continuous at 0, whereas eta b is not. That means only eta b star has that defining property that I explained for that simple illustrative example. Again, that is not a proof, but that's simply intuitively saying that what you do makes sense. And if you want slightly more proof, there are more proof of the fact that this your visual impression and the value you get are kind of consistent with each other. You can see the paper there in the pictures to show that that does happen. All right, so that's about the quantification of asymmetry. How about testing for symmetry? Testing for symmetry, we have me and Chris Bartlett, it was his PhD dissertation. We developed a test based on the necessary condition, not on the necessary and sufficient condition. I think I will give the reason that one very quickly. So, instead of having eta b and eta b star for the test, I am using notation only eta, so that's fine. So, to develop the test, we know that what eta was. Eta was simply a correlation coefficient between your density function and a cumulative distance function. So I find a sample analog of that one. That is what the top line is. That is eta hat. You can see the numerator. It's simply a covariance, isn't it? That is covariance between the density function, cumulative distance function, minus its n times their mean. But only thing, I do not know density function, I do not know cumulative distance function, so I replace them by their estimate. And that estimates are now smooth quantities. So f hat is a kernel density estimate. Your f hat could be a smooth estimate or your empirical distribution function estimate, any of those non-parametric estimates. And similarly for the denominator, and I have eta hat as the estimate of my measure of symmetry based on the necessary condition. So what do you expect? You know the statistics, the common sense. If my I can find simply putting my values of eta hat are close to 0 more often, then I have symmetry. If it is too extreme, it may not be symmetry. But how far is far, how close is close, we got to derive a probability distribution of eta hat. And I think that is what I will be doing here. Yes. So here is a mathematics behind that one then, which says that if you have a sample, some conditions, etc., then your estimate eta hat, a non-parameter, there is no parameters here. Your eta hat minus eta has a normal distribution asymptotically, and moreover, there is no h involved. I do write the bandwidth, so I never said anything about the bandwidth, but anybody who's interested in smoothing, there's a bandwidth parameter comes in, but there is no need to talk about that one. So simply my estimate of the eta has asymptotic distribution, right asymptotic distribution, so I can use it for the test. That's what. Okay. Well, then I said, yeah, I did the test, but there are lots of tests. Let me see how the test that we came up with compared to the test that we have. And as I said, there are now here I say eta 1, eta 3, eta 2. So okay. So there is a eta 1, the Butler measure, the Rothman measure, the Booth measure, and I have the test based on all those quantities also. Those actually 69, 72, 82. Those papers are actually testing for symmetry. Then there are more tests. Actually, the most popular one is probably Gupta 1967, a test of skewness based on this quantity, but that is used for the symmetry as well. And Randall's triple test for the symmetry. So there are total, yeah. Then this Antill's test. Oh, this is based on the rank procedures, and this 1996. There are almost 6-7 tests we considered, and we carried out the simulation to see how these tests perform. As it turned out, all these tests, 6, 7, 8 different tests we did simulation, all these tests do a wonderful job of detecting the symmetry. The only difference and the important difference between the tests we developed and those tests is following. These tests do not, the test statistics they use do not quantify asymmetry. They only detect the departure from the symmetry. And therefore, when we do the test, our power of the test changes according to the size of asymmetry. Get the point? Meaning, we can detect the symmetry for using most of the tests, but if we, for example, go from, say, exponential distribution to log normal distribution compared with the normal distribution, the power of those tests doesn't change much. Whereas the power of the test based on this correlation coefficient changes dramatically. Okay, that means power is a function of size of asymmetry. That was important, and that is what was required or asked by my friend whose works at SAS. Okay, so again, simulation shows that what was expected. I'm going to repeat what I just said. All the other tests do a good job of detecting asymmetry, but the powers aren't function of the size of asymmetry. But the test based on the sample counterpart of this correlation, sorry, covariance or the correlation coefficient has much better better power and increases with the size of oscillator. Well, and then we submitted the paper, and the referees are very impressive. They said very happy with the simulation. They said that will be good work, etc., etc. But there is a test which we didn't know at the time. There is a test by Lay and Pendeneville in 2009, and the same authors again, a new author with that one, 2008 and 11, and they had done with the same intention that we had, but slightly different. The power of their test increases as the asymmetry in the specified class of alternatives or a probability distribution, not any distribution. That's the important difference. And there is no guarantee that this, because the theorem doesn't cover those things, so there is no guarantee that this test will do the similar kind of thing that we do. That means our test will always have our power will always increase with the size of asymmetry. That is not there. And moreover, that class we showed that is quite restrictive as well compared to what we have. And well, that was the criticism we got. We responded with studying those things, and that the paper was accepted. Okay, so now we'll wonder, why not, if a test based on necessary condition we use, again necessary condition is a good test, but it's a necessary, it's not necessary and sufficient. So we thought maybe we should have a test based on a necessary and sufficient condition. That might be a bit better job, that might do a good job. But it seems you know that what the necessary and sufficient condition is. Each, for example, your necessary condition has, if you look at the first line, has p equal to 1, only one correlation coefficient. Right? Here we have to find for every p one correlation coefficient, again do all the things that I'm saying there, and then study the distribution. Mathematics is wonderful. We can derive the distributions of the sample counterpart of this eta b, which is a necessary and sufficient condition, but, and that is very good mathematics. We did that one, very good mathematics, but that seems too complicated to understand. Any user want to see simple, symmetry, you compute that measure and then you have to test. This doesn't work. But and moreover, and second problem was statistics. Then we may not have enough data to estimate rho p for every p. Well, we have to make a choices that okay, p equal to 0.1, 0.2, 0.3, 0.4. What are the p's we have to take? There's the extra thing is involved, and that is not very. And even if you do that one, we don't have that much data to estimate all those. And therefore, we thought we agreed that the mathematics is okay. We're going to submit the paper only on the mathematics, but that we're going to say that the test derived is not. It does better, but not that better than the test based on the necessary condition. Okay, that is about univariate symmetry. And then we thought, well, why not go to a bivariate symmetry? Well, actually multivariate symmetry. But you think about multivariate symmetry, and then I have completely no understanding about the pictures, how they look in 3 and 4 dimension, about the symmetry. Well, actually 3 dimension. When you have random error 2 dimension, the density is in the 3rd dimension, right? So you have 3-dimensional variable, the density is in the 4th dimension, and it's very difficult to imagine. Then it's very difficult to convince somebody that, oh, this is my number and this is my symmetry. It's not very useful. So we decided to stick to our attention to bivariate symmetry. Moreover, applications in finance were only for a bivariate case anyway. Now, bivariate symmetry, again we started right from the beginning. There is a lot of discussion on the bivariate symmetry in literature, but I thought, well, we'll carry on exactly the where we left the univariate symmetry. Meaning, we consider a bivariate distribution and said, okay, let's find the conditional density, which is the univariate density. So, if each conditional density is symmetric, each conditional density, that is f of x given y for every y and f of y given x for every x, then you have a general bivariate symmetry. And incidentally, this is we haven't read any paper, we just started thinking, but incidentally, that is what the definition of bivariate symmetry is. That is a paper by Nelson in 1993. Again, we didn't know that one, but our attention was drawn to that one, and that's exactly the case is. And the next one is from bivariate symmetry, symmetry about a line, meaning what we'll have is condition number AI, A2, and on top of that one, what we need is for every y, your fxy should be equal to f of minus x, y. And that will be symmetry about a line. Then we have a bivariate symmetry plus central symmetry, which will be your, again, first two condition, I to I, and then we need extra bit, which is your f of xy is equal to f of minus x and minus y. It's very easy to see. If you plot a two-line, if you say the part B, what we are saying is you minus x and plus x. You go y-axis in between, you go minus x plus, and the value is same. That is about symmetry. Of course, this is about the axis, but you can make it around any line. Or this is central symmetry, meaning you take the density function, which is the first quarter, third quarter is same, second, fourth quarter is same. Actually, all those points are the same anyway. But that is not circular symmetry. Okay, then next we have bivariate symmetry and elliptical symmetry, meaning we have again those two conditional densities are symmetric. On top of that one, constant, your density function is constant on elliptical contours. And finally, the most restrictive would be circular symmetry, which will be again first two condition was constant on circular contours. Okay, all these things are described in one of the paper, and bit more on that one. That is Riha and Patil. Riha is just finished a PhD. Okay. All right. So once we understood what the symmetries are, we said now, how about we develop again similar kind of thing. We develop the test of symmetry, or we quantify the size of symmetry. When we develop the test, can we have a test which has the same property, like a power is a function of the size of a symmetry? And so we said, well, why not start with a general bivariate symmetry and see whether we can develop the similar kind of test that we developed in the indirect test. Yeah, and then we need lots of notations. Let me discuss the notation first. Your xi yp denotes the kind of quantities we have earlier, but those are now for marginal distribution of x and y. That is, extra bit added here is suffix x, suffix y, and then extra suffix x are added on next line, which is the conditional quantity. That is, xi suffix x given y and p will be pth quantile of a regression function of x given y. And we can reverse the role, and you have y given x also. So your p equal to half, what we'll have is xi x given y half y and y given x half x. These are basically median regression, right, of y given x and x given y. And if you take if you solve this two simultaneous equation, then you get the median. Okay. That is simply trying to explain what the bivariate distribution looks like. All right. So with that one, we can define a bivariate symmetry in terms of the formulas, whatever we just said earlier. The first, a general bivariate symmetry is nothing more than that. What I have done is take a conditional distribution of x given y in the first line. I have x given y half, it's a median, minus x, which is same thing as x given y median plus x, right, which is same thing as unit symmetry. And same thing for x. So I have two different kinds of conditional densities which are univariate, and that's symmetric according to my unit symmetry. Okay, those remarks are basically saying that if we were to look that symmetry in terms of the bivariate function, how would they look? That is what the first remark is. And second remark is simply swapping the role of x and y. I wrote that. Again, I repeat, those who are reading the this line, all I'm saying is that the symmetry is what I just defined there, but the only thing is, if I had to read that function in terms of the bivariate function, how it will look like. Okay, a few more remarks. That is, if your regression, median regression of x given y is 0 for every y, the bivariate PDF fxy is symmetric about the y-axis, which is we already talked about. And similarly, other rod symmetric about x-axis. And consequently, if you have both 0, 0, we have a central symmetric, or equal to AB is symmetric about central symmetric about the point AB. And I'm going to go the same way, and I said if whatever we proved for univariate, can it be true for bivariate? It turns out the same. That is, I consider the covariance function of a bivariate density and a bivariate cumulative distribution function. That's again 0. Right? So again, think about using that. That's the necessary condition. Again, can I use to quantify that one? Yes. Because since this is a covariance, I can convert into correlation coefficient. And correlation coefficient is again between -1 to 1. So here it is. So what I have to do, same thing, only I'm using some fancy notation. So I have theta rs is actually the f multiplied by capital F with appropriate power, and what I'll get is the covariance, the expected value, and variances of all those individual quantities. And that's my that's my R is the correlation coefficient, and C is the covariance between my my joint density function and joint cumulative distribution function. So if I had to do the test, same thing, and the sample counterpart that one, and derive the distribution, well, that happens. Sorry, I think as I said, I go a bit faster. So I can use the sample counterpart to estimate the size of oscillate. But before that, again I said, can I again convert this necessary condition into necessary and sufficient condition? Yes, it's possible. So not much different here. I just extended whatever I thought about univariate. The same thing I wrote it for the bivariate. If you want to read the theorem, I'll pause for a minute. Yes, right? It makes sense. If you look at the density function, what you are doing, look at the integration on the left hand side. It is from -1 to a certain point, and from the right hand side, a similar reflection of that point to the infinity, and that should be the same if it is symmetric, and that is a necessary and sufficient condition. Now I want to convert this necessary and sufficient condition into some sort of other quantity from which I can derive a measure, and that is for that one I follow kind of things I followed earlier, meaning I now define two different densities based on the original density, taking f suffix p1 p2 is what? I have original density, which is defined only up to x less than pth marginal quantile and y less than the pth conditional quantile, right? And then similarly, fp1 p2 star is exactly opposite side of that. And then find their cumulative distribution functions. So fp1 p2, fp1 p2 star are corresponding cumulative distribution function, find their covariance, and then sum them up, and they are equal to 0 if and only if my original condition is true. So this was the bottom condition, is my original condition for fxy being symmetric, necessary sufficient condition for fu be symmetric. that is converted into sum of this covariance being 0. So since that is the case, I can again say that instead of covariance first or second covariance, I can find corresponding correlation coefficient, and their sum should be 0, right? And therefore, I have the quantification, which is eta xy, which is sum of those correlation coefficient divided by 2 square. You can manipulate different way, but that is what the measure will be, which will be on the scale 0 to 1. 1 is most asymmetric, 0 is symmetric. And again the question is, does it reflect your visual impression and the value you get, do they match? Yes, they do. But again, I do not have pictures here. Those pictures are in the paper, which is appearing in Journal of Nonparametric Statistics. Okay, now for the test of central symmetry. Now what this slide says that, okay, we developed the test on this one, but there are lots of tests. The test of symmetry starting from Heathcote 1995, News and Zhu 1998, and hundreds of those tests. And even there are central symmetry, symmetry about axis, symmetry about the line. There are various kinds of tests of symmetries are there. But we thought that let's consider our test simply testing a general symmetry and see how it works. So here is the test statistics again, which is correlation coefficient and covariance coefficient, which are the sample counterparts of my the corresponding correlation coefficient covariances. And we can show that under certain condition, under certain condition, again my correlation coefficient and covariance both have asymptotically normal distribution. Right. So we can perform the test, and we have a test which has a power depending on the size of asymmetry, which other tests don't. I agree, what we had done is not comparing apples versus apples, in the sense that our test is for general symmetry. All other tests I have mentioned, they either test of specific type of symmetry, and we say, well, does their size changes with the size of asymmetry? It doesn't, but our test does changes power with the size of asymmetry. But since it is a general asymmetry, it covers those cases. And therefore, whatever we make does sense that this test is better. And referee do agree. So I think that is what I have to say about the testing symmetry and asymmetry. Any question?
Thank you, Professor Patil. Are there any questions?
The measures of asymmetry etas that you have been using, they are sort of extreme, maximum over P. So what I felt from some prior experience about similar minimum distance statistics, I felt that similar, just like Kolmogorov-Smirnov distance and Anderson-Darling distance. Anderson-Darling distance is a weighted integrated version of Kolmogorov-Smirnov distance. Behavior is much smoother than Kolmogorov-Smirnov distance. So here a similar weighted integrated version of eta can also be tried.
Of course. I did say that there are lots of different matrices we can think about it. This is a very simple thing I did. Once you get the rho P, we can use different weight function, different matrix. We haven't done that one. In fact, that is what we thought. But I guess that is just going away a bit of main interest. But I fully agree.
Because averages are much well behaved than extremes usually.
Yeah. Agree. And what else I have to say? Well, that's the point. I agree. Thank you.
think the crux of the matter, the whole analysis seems to be catching the two functions through covariance. Am I right?
Yeah.
This is the only function through which we can catch the asymmetry, or?
No, good point. Good. First thing, okay. First thing, I guess, I'll answer your question. First thing I forgot to mention following. I guess somebody from here, who is not here, doesn't agree with me at all. Professor Ettihadi. He thinks that symmetry, we don't have to measure from the median, should we measure from any point? That's what he thinks. But for my point is here, it's every time I measure symmetry, it's from the median. The reason being, when I do this one, I don't need to estimate my center and still I do it. Whereas Redfield says that no, I decide a point and from that point I measure the symmetry. So that difference I should mention it, because when I'm at his place, this is how he defines, and I suppose he must have some collaborators here, they might have done this one, that's why this remark. Okay, coming back to, no, the covariance is not the only thing actually. Instead of covariance, see, instead of f square I wrote there in one of the conditions, you can write any other function. Yeah, this condition. Now, instead of f square, you write f cube. You'll be fine.
Why you have written f square then?
Why f square, right? Because I started covariance, and that's why I stayed with that. That's what basically happened. But the question is, if I were to do anything else, what do I get? I don't know whether I gain anything or not. I do not know. And covariance sounds to be much easier to understand, and correlation and correlation easy to understand.
Actually, going back to your earlier slide, if I go back to the earlier, please.
This one?
Still. Yeah. I think the very purpose of going through this exercise is because there is a very strong relation between F and capital F.
That's right.
Yeah. What about this half? I think I just missed that point.
Which one?
Second half.
This one to here? Huh. I think what happened is there, I must have missed something. These two lines are correct. So I should have written there twice.
Could be that minus infinity is missing in the second point.
There is a typo. There is a typo.
Yeah, there is a typo. That the R is missing. The whole range is missing. From the missing, yeah. Second to second, third.
Missing, yeah.
But, last question from my side. Perhaps I conclude. The students might be interested to get at least one application of why the symmetry business should be done.
Oh, application?
Yeah.
Oh, certainly I can give application.
But before that, I have another question. See, if we go for a marginal symmetry, does it imply the joint bivariate symmetry?
No. No.
That's why the whole business needs to be carried out separately for bivariate.
The marginal symmetry does not imply.
Okay. Thank you.
Okay. Another comment is this one. Look, whatever measure I defined so far, the weak measure, the strong measure just fine. The weak measure is not all weather. There are shortcomings there. Okay? But it does the job better than a lot of other measures. There are critics of this measure as well, even the stronger measure as well, and they do not agree with me yet. But I'm sure in another year or two, when I do further work, I hope they will agree with me that that's the best thing to do. So if you see the paper, the recent paper, I have cited those critics as well, and they have a completely different view on whatever we have proposed. This one here? No.
Because it is expected value of HA.
Yeah, expected of fx.
Integral effect into HA. I think it should be only integral, because that integral x square fy dy gets cancelled.
I think my getaway clause here is, I did a mistake, I had some typo there. My getaway clause will be, student, get a copy of that one, find the correct proof. It's okay, it's something missing there.
Excuse me, sir. You are defining different measures. So if I change distribution function there, I want to see that whether its null distribution is identical. Means whatever statistics you are giving there, whether we are getting identical null distribution. Means for example, if I suppose observations for normal distribution, suppose I have observations from uniform distribution, and if I compute that measure of asymmetry, then whether both are having identical
both are zero
distribution.
Both are zero, and
no, that is true. But whether
the distribution
statistics I am proposing, whether it will have same identical distribution.
Yeah, they don't have identical distribution. They have a normal distribution, but their variances will be different because this is the result. Yeah. This is the result. And sigma square, so it doesn't matter what it is, 0 sigma square, but sigma square is defined, where I define sigma square, sorry. I don't think I defined sigma square there. So sigma square depends on the density function. So they are both a normal, but not with the same variance, with the same mean. Does that make sense?
Prakash, I have a couple of comments.
Oh, go.
At the beginning, let me thank you very much for the exciting talk and taking us through a very extensive review of the work related to univariate symmetry and bivariate symmetry.
I'm sorry, I didn't mention your paper, sorry.
Huh?
I'm sorry, I didn't mention your paper.
Yeah, you did.
Oh, you did? Okay, sorry. Okay, sorry.
Yeah, you did.
Okay.
Yeah, I was happy to see
I see, okay.
my work being reflected on your slide. The couple of comments, I don't know whether you are aware of the fact that in the invariant symmetry, your necessary condition, especially the first necessary condition in terms of the distribution function, Balakrishnan and one of his collaborators in JSPI in 2018, if my memory serves me right, they proved it to be necessary and sufficient condition.
Which one was the one?
The first one.
First one?
The first condition. Yeah.
No, it is not sufficient. We can show it.
Yeah. But I remember they proved it to be necessary and sufficient. It was also interesting, I think, for me to go over the proof. 2018 SPI, if I remember correctly. Yeah. That is the one comment I wanted to make. The second comment is, so I also want your insight on this problem. So, especially when testing either in the univariate setup or the bivariate setup, you advocate approach based on measures of asymmetry. It's the right thing to do. And obviously, you will get entangled with the density estimations of different types, right? So my question is, when it comes to a relative comparison of two similar tests having the same objective, so other than the simulation, in terms of simulated size and simulated power, are there any methods? Because methods which don't really depend on density estimation, they have a very well accepted method in terms of Pitman efficiency. So, has it been thought about, can you come up with a sort of computations leading to Pitman efficiency in the kind of work that you have been engaged with all over the years?
I'm not exactly sure, but what our point was, the power reflects the size of oscillator, and therefore efficiency concept is kind of efficient, isn't it? That itself means efficient. But if you think about efficiency, then if you think
I am talking about a kind of the Pitman efficiency considerations. I've never been looked at it.
yeah, if you
We
think
also tried for our work, but somehow did not end up with something to
I think-
report.
I think you meant the work like efficiency. For example, you sign the test based on the sign compared to the test on sign rank test. That efficiency we can derive, right? I don't think that is that I have done here. All I can, I mean, there is no way to compare that either. What I can do is show kind of, well, that's actually done. Contiguous alternative. As your size of a symmetry converges to 0, how the test perform. But that is root and power is already there.
The symmetry in particular way.
That's what I mean. That's what I mean.
Then you need to make a computation.
That's what I mean.
That's what Madhav is indicating.
Yeah.
Because that tells you how the limiting ratio of the sample size behaves.
Look at the reliability test.
Mm-hmm.
Look at the four of different alternatives.
Yeah.
Like IFRA,
Yeah.
and whatnot. This people have been able to come up with the basis of efficiency concept.
That's it. That's what I mean. What I meant is not like I cannot compare one test with the other, but for the same test, I can take up the what do you call the Pitman's alternative and compare.
The whole idea of making that question to make our young statisticians around here, so that is a gray area where probably they can work around. That is the whole idea that I thought of.
Yeah.
What is happening in the other continent?
Okay. Yeah. Okay. Yeah. Yeah. That's valid. No, a good point. I mean, our focus was narrow, but I can understand we can have that Pitman's efficiency kind of study as well.
Yeah, so thank you very much. We are running out of
Okay,
time.
thank you.
So, yeah. So let's thank the speaker.
Thank you.
So we can have more discussion during the lunch and tea break. So I think.
Sorry, I forgot to show the pictures actually. That's okay.
Now we will have the tea break. The tea break got shortened by 5. We will have the 5 minutes tea break. Tea will be served outside the hall. We'll assemble after 5 minutes for the next session. Request all of you to come within 5 minutes, if possible.
Set up my presentation.
Yes, yes.
Yes, sure.
On button.
विद्यार्थ्यांना सूचना आहे, लवकर बसून घ्या. So, students, please settle down quickly. So, we'll start with our second session of Professor K.S. Madhavrao. I request Patil sir to chair the session and I hand over this charge to Patil sir. Thank you, sir.
Warm welcome to second half of the first session, and we have somebody I know from 1983 or 1982 for 40 years, and I did expect him to do as good as he's doing now, but I didn't expect to meet him, and I was very, very pleased to meet him, and very pleased to know the following thing, that he's still academician and he loves teaching and he loves lecturing. And his name is K.S. Madhavrao, and you have been introduced to him, so I don't need to say much about him. He is going to talk to you on market sentiments, paradigm, probability model based inference. Thank you.
Thank you, Prakash. After a break, I think it's good to start the second lecture. As you can see, I am going to talk on a topic which most of us may be very familiar with. I am very sure my senior colleagues would have definitely have few exposure in terms of investment in stock market. I don't think the younger generation is also not far behind. When I talk to my students in Mumbai, most of my students are very familiar with the market, stock market, and also they do invest on not only the physical stock but also some of the digital stocks like Bitcoin and whatnot. I have chosen a topic is interesting. Everybody in this audience, not only the students out, and also the content can be easily understood by most of my student friends here. It is very conscious decision I chose to talk on this particular topic. So let me first start with a small story about how I got myself interested in this area of statistics. This was in Botswana, where I spent around 15 years before coming back to India and continued at Shivaji University. I had a colleague there. One day he walked into my office along with a gentleman who happened to be his classmate, the master's course, And also he was working in the stock market body in Botswana, known as the Botswana Stock Market Stock Exchange, DST. He wanted to understand some of the statistical techniques used in stock market data. Botswana doesn't have the scale of the stock market that we have back in India. It's a small country, it's a small economy. Obviously, the stock market operation will also be of a lesser magnitude and scale as compared to India or other emerging economies. Well, in that the stock market, there were hardly something like 30 domestic companies and maybe some 5 to 6 foreign investment companies. Just juxtaposition, compare that kind of economy with the Indian economy that we have here. So they were very keen to understand the different mechanisms that operate stock market data on a day-to-day basis, on a weekly basis and monthly basis and annual basis. So my colleague had a lot of done engaged with certain related work. He came up with a lot of papers, and most of the time these stock market data, they are, as all of us know, is the time series data. I am very happy that we have an expert here, Mr. Ramanathan, time series data. Usually people talk about forecasting or predicting future return stock market data, that they use sophisticated mathematical techniques, techniques that even won Nobel Awards. Like for example, later on Ramanathan will tell you about some of the models that are very popularly used in financial statistics, like DAX model, ARC model. These are the models. You know that the ARC model was discovered by Engel and others, won then Nobel Award also. But my client, so they were not very much impressed, rather inclined to follow that route. So they were very keen to compel on us whether they can come up with some easier methods where they can quantify the market sentiments, and also can they come up with some hypotheses about the different patterns of market sentiment, and whether some statistical techniques can be used to validate these hypotheses. Okay, this was the starting point. So they wanted to take a different route than what it was practiced at that point of time, and even now it is being practiced world over, and more sophisticated mathematical techniques are coming up to forecast stock market return. So in this paper, in this talk, I am going to slightly deviate from the traditional approach and come up with a new technique which in fact makes more meaningful and also provides an alternative way to look at the stock market sentiment analysis. Okay. Well, I am going to talk about the following contents, with the brief introduction, the concept of market sentiments, the hypotheses related to market sentiments, then how do we go around testing these hypotheses of various kinds related to the market sentiments. Then we look at some application to DST censored data, and finally some conclusions where I would implore my younger friends, students, some of the take interest in this particular area, and look at some of the open area, some of the gaps which I might point out subsequently, so that you can think about them, follow it up for your PhD study, or maybe even for my younger colleagues in the Department of Statistics here, so we can also think about trying to fix this gap. Well, few basic concepts that all of us know very about as the statisticians. The variation in stock market prices due to daily price change is generally termed as the volatility. So the volatility is usually a function of the standard deviation. So most of the people or research in the area of stock market data is always centered around this volatility. Like I said earlier, there are several approaches to deal with the volatility. So as we know, the volatility is both good and bad. If the swing is upward by a magnitude which is disproportionate to your expectations, obviously you are going to make a lot of money. On the other hand, the swing is towards the lower end, and obviously you are going to lose your investment over the period of time. So therefore, volatility is something that we need to always care about. You have to live with it, and also in station you have to deal with it. What are known as the company profiles. They can come because of the company profiles. Sometimes they can purely come because of some of the opinions that are out in the public domain. Some of the information, the news information can also trigger the variation in either directions. So this is why most of the times this volatility happens in stock market data. I already dealt with this, the reasons for volatility. So the central theme of my presentation is to suggest an alternative method of dealing with the volatility, which is in terms of stock market sentiment analysis. That subsequently this approach can be applied to weekly data, or monthly data, or annual data, or daily data, and we essentially conceive or have a perception of this volatility in terms of some classification based on the market sentiments. I said in my opening remark, the literature on economic and financial variable data analysis is quite extensive. Not my purpose to give you over the vast work that I have done in this area. But anyway, like I said earlier, two important work that eventually triggered this approach to analyze stock market data is from the work of Angel in 1982. Subsequently, we also looked at the DART model, which subsequently was developed by this group of collaborators, workers, and some of them are students as well. So those of you who want to look at this approach can refer to a book by Blake and Sheldon. Like I said, there are really thousands of articles in this area. One need not really go to the journal articles, but all these developments have been very nicely captured in several textbooks. For a beginner, I would like to recommend the book by Blake and Sheldon. One of the fundamental concept of market sentiment is was the one proposed by Edwards sometime during the year 2001. So that simply deals with the sentiment analysis regarding the daily trading series, and that is based on a concept called refutal theory. Most of the people who are working in this area are very familiar with the refutal theory. So the refutal theory is simply underlying the following facts. You have the formula for the pivot points. As you can see, there are 5 market sentiments. So in the middle you have the pivot, which is simply the simple average of high, low and close on a trading day. And you have 2 resistance levels, R1 and R2, and also you have 2 support levels, S1 and S2. So this is one of the simplest and probably the most used technical indicator based on the pivot point. So look at most of the dashboard, most of the financial supporters, definitely they will talk about this. They will generate graphs based on this pivot point technical indicator analysis, even for the monthly data or for weekly data. By click of the mouse, you can have all kinds of this technical data. So if you look at the pivot point analysis, it usually helps a trader who is interested in day-to-day investment. So if the stock market is up, obviously he will sell his stock. If it is down, probably he will hold on to it so that whatever the money that he has invested in the subsequent period. Okay, but what happens in the pivotal analysis, based on our experience, when we especially applied this pivotal analysis to the stock market data in Botswana, we found that typical company indices, they don't capture all the sentiments. So it's possible that some of these market sentiments will not be present even in a there are ample evidence to see that this pivotal point analysis simply collapses because market some of the company indices may not have these categories of market sentiments. So with this idea, we thought about something different so that such a situation is not confronted or is not seen when you properly devise market sentiments. So we came up with 2 types of market sentiment, namely absolute market sentiments and relative market sentiment. So absolute market sentiments can be defined with reference to a base period usually greater than a month, such as a quarter of the year or biannual or annual. In this case, market sentiments are constructed based on the entirety of data corresponding to certain base period. Usually you can take this base period as 1 year. So to fix our idea, an example would be something like if one wants to study daily, weekly market sentiment based on stock market prices in a given year, we pointed out that the absolute market sentiments are useful to compare the movements in market sentiments over blocks of years, hence may be of use to players with the long-term investment interest. So this absolute market, if somebody foreign institutional investor wants to come enter into a market, obviously he is not worried about what is happening on a day-to-day basis or weekly basis or even a monthly basis. We would like to see maybe in a horizon of 5 years or maybe 10 years how the market is going to react to the different factors that affect. So they would be actually looking at the absolute sentiments. On the other hand, one can also think about relative market sentiment, that these sentiments reflect the shorter variations, the variations such as happening over a week or a month. So in this case, market sentiments are more dynamic in the sense that constructs compare weekly or monthly data from time to time. So relative market sentiments are seen to be useful to an active player with the short-term interest, especially those trading individuals or trading the companies who wants to make quick bucks by investing on a day-to-day basis or weekly basis. So what they should be looking at is the absolute market sentiments rather than, relative market sentiments rather than short absolute market sentiments. So based on our initial investigation with our clients, so my colleague Boseki and me, we outlined the difference between the volatility phenomena and the market sentiment paradigm. It was very important to push our new idea in scientific journal. So therefore, we needed to build a case by strongly emphasizing the difference between the classical approach in terms of building a time series model and also the approach that we are proposing as an alternative. Okay. So these are the characteristic difference between the two approaches. Volatility is a continuous variable while the market sentiment is invariably a categorical variable. So volatility is usually measured in terms of statistical concept of dispersion, while the market sentiment is defined on the basis of classification criteria based on the original price index. So market sentiment states can be defined purely on the basis of perceptions also. So most of the times they are without any valid evidence based strategy, they are simply defined based on the perception also. So we give below the definitions of absolute and relative market sentiment states of daily returns. So I am going to look at few definitions now. So these definitions are in line with the introductory discourse that I have been engaged with a while before. So let Fk be the class of all states S1, S2, Sk for daily equity indices data set X. Then Fk is said to be a class of absolute market sentiment states with the states, the members in the states Si belonging to the class Fk is induced by a classification rule Ri that compares each Xj in X with a suitable measure constructed using a function of Xj minus I and the entire data set X. So this is what we essentially do in absolute market sentiment definition. Suppose if you have entirety of data, then you look at a previous data, then construct a function of the entirety of data and propose a function and see how does it compare with the current day's price index. So based on that, you can come up with a absolute market sentiment definition. These are the values. That is the time series data. So the above definition implies that the absolute market sentiments are generated by simply mapping your the price data over the period of capital N into a class consisting of categories S1, S2, etc., Sk using the classification rule Ri based on its immediate past along with the function of the entire data set. So this is what we essentially do in coming up with a classification rule for the absolute market sentiment. Well, I have a couple of examples here. So those of you are interested, we can discuss that after the presentation. So here we have a classification based on a certain function. So R1 is a classification for the first state, and Ri is a classification rule for state 2 up to state k minus 1, and Rk is the classification rule for the state k. Small typo, I equal to 2 to k minus 1. Now let's look at the relative sentiment here. Now what I mentioned in the beginning, so the relative sentiments are designed by keeping in view the trading requirements of a short-term player. The people who trade daily or maybe weekly, so they will be more concerned about the relative market sentiment than a person who is interested in long-term investment. Okay. So look at the definition. So again you have a class Fk of states S1, S2, Sk of daily equity indices, and then Fk is said to be the class of relative market sentiment states if the state Si is a member of Fk induced by a classification Ri that compares each x in xj, that should be the other way around, compares each xj plus 1, j equal to 1 to n minus 1 in your data vector x is a suitable measure based on the peak lag data set. You have a lag data set now, which is denoted by xp vector xp, xj minus 1, xj minus 2 up to xj. Oh, sorry, xj minus t, comma dot 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 xj, where this t lies between 1 and p. Okay. You are actually looking at the functions of the previous lag data. So that is what you are using essentially in the relative market, the sentiment. So I have an example similar to the example of absolute market sentiment, where your lag length is 2 and you are looking at 3 states, namely S1, S2, S3. So this is what we essentially do. We construct certain functions of lag variable so that you can come up with a classification rule to come up with these states, which are relative market, which reflect relative market sentiments. So I will give you an example now of how to construct the market sentiments based on absolute market sentiment and relative market sentiment. Maybe a 5-state market sentiment and also 7-state market sentiment. So later on we will see in the application of these methodology for practical data. Most of the time people are happy with the 5-state market sentiment, like just like the reference I have made earlier, namely the technical indicator based on pivot points. Actually it is a 5-state market sentiment. And one can also look at the 7-state market sentiment. We will see how they can be formulated. So you have this data set and you compute your x bar and s square as described in this slide. Suppose if you are looking at a daily market sentiment, so this could be the possible way of coming up with the 5-state market sentiment. You simply look at your, so for the day I plus 1, the equity index is said to belong to state 1 if xi minus 1 is less than xi minus 2s, then xi minus 2s is less than xi minus 1 less than xi minus s. So we are essentially taking 2 standard deviations. Suppose if you want to have let's say a 7-state market sentiment, probably you can work with the 3 standard deviation. That is how you can go from 5-state market sentiment to 7-state market sentiment. On the other hand, you can accordingly come up with a relative daily market sentiment in a similar fashion. So let's look at an example where we have an example of a 5-state market sentiment reflecting the relative sentiments. So you will notice that your classification rule is based on 2 variables here. So you are comparing your xi minus xi and xi minus 2. You are looking at the function based on xi and xi minus 2. And again, here you are essentially looking not based on your S, but there is another criteria where you look at 5% increase or 2.5% increase, which is arbitrary. I will tell later on why you need to look at 5% increase and 2.5% increase as the constant that you need to use in this classification technique. Well, most of the stock market analysis, they use these, they name these 5 states as bearish sentiment and S2 as the downward of the decline sentiment, and S3 is usually termed as the tranquil sentiment. This is our pivot, something like the pivot, and your S2 and S1 in the pivot technical indicator, they are popularly named as upward or inclined sentiment, and your S5 is the bullish sentiment, which is synonymous with the S2 that we have seen in the technical indicator. Okay. Well, now the question is, how do you model these market sentiments? So, a natural the probability model that comes up to anybody's mind is just build a multinomial model. So that's what we essentially recommended. So you build a multinomial model based on your data, then multinomial model with the K market sentiments, and this K market sentiments, the probability, you have a classification rule Ri, which will tell how a given data point has to be classified into any one of these A classes, and that will lead to a multinomial probability model given by this Px theta, with obvious the conditions that your xi should be bigger than 0, less than n, and total of this xi should be equal to capital N. Capital N is missing out, and these thetas are the probabilities and inclusion probabilities essentially based on that the classification rule. So, like I said, what next after building up the market sentiment, the model? So, based on our interrogation or interaction with the client from the Botswana Stock Exchange, we figured out they are interested in several types of interrelationship between the sentiment probabilities, some kind of relationship between the sentiment probability. Like I said, the Botswana Stock Exchange had around 30 domestic companies, so it was easy to get the data on individual domestic companies and really look at their pattern and see what insight can be brought into analyzing the data. So our experience showed that based on their data, one can come up with several types of relations between these inclusion probabilities. So we talk about the first definition, where we essentially visualize a market sentiment which has a symmetric underlying pattern among thetas. So we come up with a definition of equisymmetric market sentiment. It says that a K-state market sentiment class is said to be equisymmetric if and only if all thetas are equal. So that makes sense, right? So there are companies which don't show any price movements over a long period of time. The companies, maybe the companies which are just floated, which have just come up with the IPO, for obvious reasons, they don't show any the price movements systematically over a long period of time. So Botswana Stock Exchange company, they wanted to identify such companies with some validation through statistical methodologies. So that's why we came up with this hypothesis or this definition. Then there are other companies which show over a period of time there is a variation, but the other period of time though they stay more or less on a equisymmetric fashion. Therefore, that necessitated us to come up with a definition of partial equisymmetric market sentiment, which simply says for some theta, you have theta equal to 1 over k, and for I equal to 1 to t, where t is less than some k. The next is the interesting pattern, which is a complete symmetric market sentiment. A K-state market sentiment class FKCS is said to be a complete symmetric if and only if. So these are all the characterizing properties. If and only if theta is equal to theta k minus I plus 1 for I equal to 1 to k. Then again you have an analog in this definition, which is a partial asymmetric market sentiment. So what it simply means is for some t, these thetas are more or less the same on either side of the point of symmetry, but they are different for other t. So this is what exactly the hypothesis, the definition says. So also you have the invariant market sentiment states. So this invariant market sentiment says if you have different types of classifying market sentiments, like absolute market sentiment, then say relative market sentiment, or maybe the market sentiment which is gotten by applying the pave point technical indicators. So can we say that all these market sentiments classification rule essentially end up with the same result? So this is what we mean by invariance of different types of classification rules of arriving at market sentiment. So this was also something which was which was interesting to the client. So there was a necessity of coming up with a definition of this kind. Then I think stationary market sentiment. I will not talk about this now. Okay. So obviously, this definition lead to some of the formulations of hypotheses. Okay. So the client wanted whether the company is registered under Botswana Stock Exchange company, in fact, show up these kind of market sentiments, the relations between the inclusion probabilities in the model. Okay. So let's talk about some of the hypotheses related to the market sentiment. The first hypothesis is equisymmetric market sentiment. It simply says your H naught is theta equal to 1 over k for all I versus the alternative, which is simply the negation of H naught. Okay. Again, you have the partial equisymmetric market sentiment, which simply says your H naught is theta is are equal for some t, but they are different for some other t, where this t is less than the k. Okay. Then the next hypothesis of interest is the complete symmetric of market sentiments. So they can be simply carried out by testing whether theta I is equal to theta k minus I plus 1 for I equal to 1 to k against the negation of this H naught. Okay. And again, you have a slightly different hypothesis where we wish to test the complete symmetry for some values of k. So that's why you have h naught theta equal to theta k minus I plus 1 for I equal to 1 to k for some t, and where this t is in between 2 and k. It should be 2 and k. Yeah. Versus the alternative, the negation of h naught. So a similar hypothesis can be framed about the invariance. You want to see whether the market sentiments model obtained by different types of classification rule in fact lead to the same model. So that is what is reflected in the hypothesis h naught, and h1 is simply the negation of this hypothesis. Well, similar thing can be done about the stationary market sentiment. Okay. Now, the one thing that I want to mention here is all these tests can be, the validated hypothesis can be validated with the simple statistical methods that we usually teach in our master's program. Okay. So the likelihood ratio test, then the chi-square goodness of it can be simply deployed to test different types of hypotheses that we are studied about. So that shows the simplicity of the market sentiment approach to tackle the problem, especially related to the stock market data. So all that you need is to obtain the maximum likelihood estimators under the H naught under the restricted hypothesis, and also you find the maximum likelihood estimated under the unrestricted hypothesis. Then you simply look at the likelihood ratio, and a little bit of algebra will take you to the final form of the test statistics. That's what is being done here. So I will not go into the details of the calculations because they are very straightforward and routine. Even my student friends can actually give it a try to verify the formula that you can see on the board, okay, on the slide. Okay. So let me first look at the first hypothesis, namely testing for equisymmetry. Well, you can see the likelihood ratio test statistics essentially boils down to that lambda ES, and you can also these are all chi-square test statistics. Asymptotically, they are all chi-square. It's not very hard to prove each one of them. Then you can also look at the equivalent test statistics based on the chi-square goodness of it. They can be derived very easily. Of course, they have two different forms, but asymptotically they are equivalent. Okay. So, Prakash, how much time do I have now? 5 minutes. Yeah, that should be good enough. So, when we talk about the partial equisymmetry, again the same mathematical the details are required to arrive at the test statistics based on likelihood approach as well as the chi-square goodness of it. This is for testing for complete symmetry. Well, so you can see they are very easily implementable. You can calculate them even using desk calculators or hand calculators or maybe simple commands. Excel can be used to compute these things. And the interesting point is it is possible to integrate all these computations along with the technical indicators. If one wants to further augment your dashboard in most of these financial the portals along with the technical indicators based on pivot method, you can also create a dashboard based on these statistics. You not only have the visual analytics of this analysis based on pure indicators, but you can also have a quantitative measure of different types of market sentiments. Okay. So I don't want to go over and over again over this method. So the point that I want to make here is that you can come up with the proper statistical test method where you can carry out the test of all these different types of market sentiments, namely weekly market sentiment, then partial liquid market sentiment, then complete market sentiment, partial complete market sentiment, and also you can test about the invariance over a period of time, stationarity over a period of time, and the invariance between different types of market sentiments. Okay. Yeah. So we, apart from, unfortunately, I don't have the analytics, visual analytics, and the summary test statistics carried out for the Botswana Stock Exchange. So I lost that file. But anyway, you can, the students can try out these methods for daily Sensex index or weekly Sensex index and monthly Sensex index. So you all know all these data are available either in DST portal or maybe M.Sc portal or maybe Yahoo Finance. So all these data are available. You can actually carry out these test statistics and see whether either for the census or maybe you can catch hold of company indices. The company indices are also available. Maybe we have to become members of these portals. Which are very, I think, a very small amount annually. Then you can try out all these information based on the individual companies also. So, I quickly summarize the conclusions based on analysis of these companies. So, some of the companies in Botswana, in fact, belong to all the four categories of market sentiment that we talked about. Okay. So, a similar pattern we see in some of the companies in India. Unfortunately, I don't have the summary table here, but similar findings are seen in while analyzing the market sentiments related to some of the companies in India also. Okay. The one important thing, a gap that probably students can, or my colleagues can work on. See, usually there is a pattern among the data. If you look at the empirical data, either related to the market sentiment based on, related to DST census or maybe Nifty, you can see there is a pattern. If you classify according to any one of these classification rules. So the question is, instead of having a null hypothesis, we say theta I equal to, let's say, if I look at one hypothesis, the theta 1 is same as theta 5, and theta 2 is same as theta 4, then, so you essentially have a complete symmetry hypothesis, but in the null hypothesis, we are not reflecting the order. We are reflecting the order. There may be order between theta 1 and theta 2. Similarly, there may be order between theta 3 and theta 4. So one actually should look at the ordered null hypothesis as well as the ordered alternate hypothesis. So this is more appropriate by looking at the empirical data. So in the scenario of where you have ordered alternatives or the ordered null hypothesis, obviously your test statistics are going to be different, and you need a different approach to come up with a test study. This is an open area. This is a gap where some of my student friends or researchers can work on. So with this I end my presentation. So thank you for listening, and if there are any questions, I will be very happy to take them.
Any questions? Questions? Yes, sir.
This is assumed to be independent or it's assumed to be a Markov chain? I mean, moving from one state to other.
They are independent.
So that is probably there is the one area you can also look at. Okay? The dependency pattern can also be looked at. Right now we have not looked at that area or possibility. Yeah.
Whether the concept of quarterly result or share purchased by foreign investor, and if they have sell out, so what such type of events are considered while in this strategy?
Sorry, I didn't get your question. Right.
My general question: if Tata Motors have declared their quarterly results,
okay.
So if their according to their quarterly results, so suppose they have shown losses. So such type of events also some foreign investors have purchased the shares, and if they sell out drastically, so it then the shares prices will be goes down.
It will definitely go.
Yeah. Such events are considered while considering this strategies.
Yeah, definitely. On that particular day, so there is a classification rule. When the prices fall, obviously it will change the market sentiments also. Correct? You see, for example, if you are looking at Tata Motors, the case in point that you are talking about the Tata Motors, right? So obviously, if they declared their quarterly results, obviously that news information is vital to the investor, right?
Yeah.
So obviously, he may start selling his exposure to that company, and obviously the prices will fall down, right? Isn't it? So obviously the Tata market company's market sentiment state will change because it is captured by the classification rule.
Thank you so much, sir. I thank Prakash Patil, sir, and K.S. Madhav, sir. We have the announcement. Now we have the lunch break. The lunch is served at the university guest house, which is after the ladies' hostel. Those who don't know, I request the students from M.Sc 1 or 2 to please guide the participants. We'll assemble here sharp at 2:45 for the next session. I request all the participants be on a time so that we will start our next session on time. 2:45. Thank you. Sir. Yeah, it's not here.
हाँ ऑफ कर येते काय झालं केली की बंद केली Hello. 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 Is it? Hello. 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 Hello.
Check. Hello, 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 check. Hello, hello. Check. Hello. Hello, hello. Check. Hello. Hello. Check. Hello. hello, hello, cheek, hello, 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 cheek, hello, 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 cheek, hello, 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 cheek, hello, hello, hello.
Hello, hello, hello.
Good afternoon. I request students please settle down. Yes, pointer. You are? Pointer? Pointer. So you have noted? Yeah, controller. Good afternoon all. I welcome you all for the third invited session.
Backward or forward?
Yes. For the third invited session, we have Professor T. V. Ramanathan sir. I request Madhav Rao sir to chair the session, and I request to take a charge of this session. Yes.
Thank you. Welcome back, everybody. After a very sumptuous dinner, we cannot think of any other digestive tool than to hear Professor Ramanathan taking us into the world of time series analytics. Today's speaker, Professor Ramanathan, is known to me maybe for the last 3 decades. First, I came to know him as a young researcher at the Department of Statistics in Pune University. So he completed his PhD by turning out a thesis which can be a model to everybody. So he did such wonderful work under Professor Rajeshri. And I hear from my teachers and also the colleagues that Ramanathan's work was a trendsetter in those period of time. Okay. So he also worked as a teacher, that is he started his career as a teacher at North Maharashtra University in Jalgaon, and after getting his the PhD, he went to the University of Botswana, and for obvious reasons he came back, because Botswana is not a place for young professionals like him. Only people who are starting their second innings can go there and contribute to the education sector in that country. For right reasons, Ramanathan came back and joined the Department of Statistics in Pune University. As we all know, from the position of assistant professor, he rose to the professor's cadre, and he became head of the department, and he is discharging his duty very efficiently the last couple of years. Okay? And no wonder he is fascinated by time series analysis, and I guess he had an introduction to this field when he was working in Reserve Bank of India. The time series is a very, very important area, especially people dealing with the fiscal and monetary issues. I am very sure his short stint at RBI must have opened up new thoughts in the time series analysis, and that's why he decided to continue his research work in the area of the time series. Okay. Professor Ramanathan is a very active researcher. In spite of his administrative responsibilities and teaching commitment, he always makes his time to devote his time to the students, so that he believes in mentoring youngsters. The legacy should continue. It should not end with a person. So he believes in sharing his knowledge with the youngsters, and that could be easily seen by the turnout of PhD and MPhil students over the years. So he has successfully graduated 3 MPhil students and 8 PhD students, and I'm very sure a couple of them are, couple of more are working under him currently. He has a wide area of research interest, starting from the classical inference in stochastic process, finance and time series analysis, non-parametric inference, financial econometrics, and notably the all-pervading big data analytics. So that is the buzzword now. So he has laid his hands and doing some productive research in that area also. Okay. I am a very good friend of Professor Ramanathan, and I am very happy to chair a session that is going to be given by him, and I deem it as my privilege to chair the session. Over to Professor Ramanathan.
Thank you. Thank you for the good words. I hope you won't sleep. The last question so that you are awake. Yeah. So, at the outset, I would like to thank the organizers for inviting me for this symposium. So, I would basically start with first few 10 minutes, and not meant for the teachers, it's meant for the students. Okay. And then we will go back to the presentation. So, I want to start from where Professor Shirke stopped. If you have data, x1 next to xn, what is the first thing that you do in an undergraduate class? To know how the data, how it look like. You start drawing the histogram, right? Histogram, descriptive statistics, etc. But here we are more interested in the distribution. So I will be looking at the histogram, and then you have learned what is called frequency polygon. Join the midpoints of that histogram, and then you get the frequency polygon. Now, if somebody asks you, if I want, of course, those who are in the second year of M.Sc, perhaps you might have seen what I am going to say. If, for example, in your class that you want maximum likelihood estimator for a suppose you have data from a particular distribution, and then you want to have a maximum likelihood estimator. So you know how to derive it. You write the distribution and write the joint or the likelihood, maximize it, and get a theta hat is equal to some function of x, right? Now, I would like to ask the question here. The interest is this f. So I want to have an estimator for this f. Now I know that many of the students, some of you may be knowing that already, but some of you may not be. So this is the point where we start, and that's what Professor Patil was telling today morning. So Shirke sir was also saying the same thing. So we want to have this. So is it possible to obtain this at some particular point? So we can obtain it. There is something like there are some unknown things here, and anyway you know that is the number of sample size. There is a h, there is a k. What are these things? This h is actually what we call it as, so in a histogram you draw, you take the bin, isn't it? You divide that, and then what should be the width of that. So something similar I want to have, which actually depends on n. So some people may write this. Then I want to have a function, we call this as kernel. It's like a density function with certain properties, which I am not now describing all the details. So this can be treated as an estimator for my f. So naturally people will ask, oh, I know the estimator, so what are its good properties? So you start looking at, is it unbiased, is it consistent, what is the variance, etc., etc. There are so many questions that one can ask. So this is where the starting point, and then now the question is from here. So maybe is it like, can you have some kind of an expansion?
which basically now I can talk about expected value of this if I have something like this, or expected value of this is approximately equal to this, or equal to this plus something. So I am not getting into the derivation, but I am just trying to tell you that these are some of the things that people are interested. And then generally we also consider variance. Now in this case, because it is biased, tell me if you have a bias estimator, will you consider variance or mean square error? Mean square error. So I would like to look at this. Which can be written as right. I would like to look at this. Now the question here is this is computed. So mean square error is there. I mean, like you can compute this quantity, and this is we are computing this at a particular point x. Okay. So we would like to know, I mean, like, you know, if your overall points of x will look like. Is it possible to have, so I have chosen few things here. Is it possible to choose this such that this is small? Like we generally do in the UMVU estimation. Which estimator has least variance? So I will go for that competing estimator. Now here I am not going for a competing estimator, but I will consider this estimator such that it actually have a h, which is a function of n, as well as a kernel, and then what kernel can give me the minimum mean square error? What hn would be better in this case? So these are some of the questions that are asked, and then this has been investigated for quite some time, and people have been working on this. Now the problem of interest is this. I am just turning around little bit and then trying to see that what is this, how this is connected with regression. So what is regression? This. Okay, call this as some function of x. So I can write this as y, right? The conditional expectation, that is the regression, the one which minimizes the minimum. Okay, so I will consider this, and then if you write this, something like this. Now what we do is that if I replace this with the estimators, okay, is it, I mean, can I get an estimator for this quantity directly? In the sense that you are all doing in regression considering this as a parametric function. You are considering it as beta naught plus beta 1 x, and then try to estimate beta naught and beta 1. And what Professor Patil and was telling today morning, that in many cases I don't, because this is something wrong. I mean, in the sense that when I am not sure, why should I consider this? Instead of that, I estimate the function itself. So this is what the flavor of non-parametric. Because I am not sure about the parametrics of that, I estimate this with a non-parametric flavor, and that's what. So here, if I estimate this this m hat, I mean this x, of course we can do some simplification and get finally as an estimator something like this. Right? This, there is a h here, so I am writing that because there is a 1 by h. Right? Formula. Then I was an estimator. Right. So that's true. I am estimating this expectation of y given x as a function of x, and it's basically, if you look at this, this is something like WIYI, WIX. So it's like a mean kind of a thing. I am giving weightage for yi depending on how the x's are, right? And that's what we are doing. And this estimator is quite famous, that is called Nadaraya-Watson estimate of the regression function. So we can estimate the function. So no problem, even if it is linear, non-linear, parabolic, no issues. And this is where the kind of non-parametric or the smoothing techniques that we have been talking from today morning actually work. So here, of course, this now we can think about, can you modify this? So there are a lot of modifications, Gas, Muller, and there are a couple of other modifications for this, various different ways of choosing the weight. You can have various estimators, and then you can compare them. All these are done. I mean, like a lot of things have been done on. The question is, if your observations are now, for a minute, let me erase all these things. Okay. So now I am going to talk for next 5 minutes a situation just 5 minutes. So now I have, instead of, I'll change the problem little bit. Suppose you have a time series. So you have time series data. Can some student tell me what is the difference between the XS I wrote earlier and the XS I am writing now? Okay. Exactly. Good. So these are time dependent. So there can be a correlation between them or a covariance between them, right? And we would like to model this because most of the time series is trying to answer this question. If I know this, what is going to be this? We would like to forecast. Okay, what is going to be xn plus k if I know x1, x2, xn? So any guess? I'm asking students. Okay. So if you consider minimizing the mean square, this is going to be the best predictor, because that you have learned regression. What is regression? The best predictor of y having the knowledge of x. Best in terms of minimizing, because you are minimizing this quantity. So on the same line, I will consider this is the best predictor of xn plus k, which minimizes that. Or in other words, now that I don't want to, I mean like we can actually write, because you have to attach to the time. So I will write xt in terms of, so I will write this as xt minus 1, xt minus 2, etc. and plus an error, which we generally call it as a white noise. So white noise means uncorrelated. Okay, mean 0, uncorrelated series. So I would like to have this particular thing. So now in a practical situation, this cannot go up to infinity. You can have to go up to a particular number. So I may go up to, I mean like t minus p. So what I wanted now, is it possible to get this, estimate this? Well, in time series class, in the linear setup, we start calling it by certain names, AR1, MA1, ARMA1, etc., and then write the appropriate functional form for this. You write beta naught plus beta 1 xt minus 1 zt, that gives you AR1, etc., etc. So the problem here is it possible to estimate this f? Not a new problem, people have been working on that. I am just doing some review, and of course with some more addition to that. Okay, so basically the interest today is this. Now, there is one more point of interest. Because I am using the board, then I will be standing there. So, I will tell that and then go there. Okay. Is it like, so this is basically you are trying to model the mean, isn't it? When I try to understand this, I am trying to model the mean or conditional mean. You can call it as conditional mean. But sometimes what happens that, you know, in regression, there are couple of problems that you face when you do the residual analysis. What is one of the problem? Multicollinearity is one of the problem. Another problem is heteroscedasticity, right? Variances are changing. Now, you can also have a similar situation in this case. So, for example, if you have a time series which goes like this and then suddenly it is like this, something like this. So, what is actually happening is that the variance may be quite large in such situation as compared to what you had in the other points. But then you have a problem. You can't go and have a variance which is completely depending on the time, because then it will be non-stationary. So, we have to be clever in taking into consideration that. So, what we do is that instead of this, maybe I will consider this as, so I will let me call this as a vector t minus 1 plus the vector so t minus 1, t minus 2, etc. So, this function, and then there is another function now we have brought in, which is actually a non-negative function, because this has mean 0. So, this is going to be the square of this is going to be the variance. So, it is kind of variance function. So, naturally you need to estimate this. Now, I mean the problem here is you can't call it as marginal variance, because it actually going to depend on the time. So, we call like this, we call that as a conditional variance. And that is what Professor Madhav Rao was talking about, the arch-guard setup, how to model that. Okay. So, there are various ways, but my interest is basically, is it possible to have these things? So, the basic interest is this function, you estimate them in a non-parametric way. Are there any methods already in the literature? Is there anything that new that be given? Well, I may not be in a position to cover all the things in 1 hour, but the idea is to throw some light so that you have some idea. Is that okay? Fine. Now, okay, so the topic is basically smoothing of in time series. So, there are two ways to do that, in time domain and one is in frequency domain. So, you may wonder what are these two things. Well, those who have done the time series course, they may understand. Others I can tell you in a very simple manner. If I have drawn a picture there. So, a mathematician and physicist generally see those pictures as in terms of a function, and then they look at the amplitude and the frequency, right? That is what they look at, that function. Statistician look at it in a slightly different way. Of course, statistician also can look at that way, but he may look in a different way in terms of, like in the time domain, what kind of random behavior it has got, how the conditional variances are changing, how the conditional mean is changing, what kind of covariance structure it has got, how the covariance function look like, can you model them? This is what generally a statistician look at. Well, so this is what one is in the frequency domain and one is in the time domain. Now, when you look at in the frequency domain, you can have, if you have done in maths, if you have done Fourier analysis or Fourier transform or even Laplace transform, if you have done little detail, you know that you can associate the variation, the frequencies in the variance, how the frequency changes as the variance changes. So, this can be consolidated as a function and how it is distributed, and that is called the spectral density function. Okay. So, I am not writing the formula because today I may not be in a position to cover that. Now, how that function can be estimated non-parametrically. So that is one area of interest. Well, this is not a new problem. There is sample estimates of that because it has got a nice formula. You can estimate them, but the estimator, if you simply consider the sample estimator, is called as periodogram. If you do that, it won't turn out to be consistent. It will have it may not have good properties. So people try to adjust it in such a way because these are defined. It's like your discrete Fourier transform. So only certain points that you get. So you try to use some kind of a window to adjust that. So there are different windows, etc. So this is one area that non-parametric functional estimation is useful in the case of time series analysis in the frequency domain. In the other case, we are in the time domain. So time domain, there are two problems. One is conditional mean, one is conditional variance. And conditional variance we call by the name volatility. Okay. Well, now the third problem is testing problem, which there are several testing problems that you can formulate using non-parametric methods, using ranks, using maybe signs, not using the actual values, even though the observations are dependent. The main difference in the case of IID and here your observations are dependent. So you need to be very careful while deriving the corresponding results and all. So there are non-parametric testing problems which addresses linearity, structural changes, and unit root. Unit root is basically testing for stationarity. Okay. So these we may not have enough time to go through all of them, but as much as possible. Professor Madhav, you can just stop me. Okay, so I'll start with the first one. So it's a stationary time series, and then if you look at this f, which I wrote there, that's my f function, which minimizes that. I think I already mentioned. And in the parametric approach, we choose some specific parametric case, and the non-parametric we allow f to be some flexible class of function, and then this is being estimated. There are two different, in general there are two different ways. One is you fix a point and then try to see, you can approximate to that function, that is what called local, around that, try to minimize the difference between the one which you are proposing and the actual one at that fixed point. And one is a global one, you don't want to fix it, but then in general, how this can be approximated. So that is the global approximation. So two ways that one can do this. Now, I already told you that we have this linear ARMA model, and that it need not be linear also, it can be non-linear also, where you can have structural changes, jumps, etc. can be accommodated. And that's what the next line. I have not written all of them. If you are interested, look into the book by Tong, Nonlinear Time Series Model, or there is another book by Say, T-S-A-Y, on nonlinear time series. So you can have a look at them, and then that gives you a lot of nonlinear time series. So the approach in those are basically approximate these things with a particular function from a class, and then estimate the parameters associated with that. Okay. Now, in the case of conditional mean, see, one of the problems that we have is there are a couple of issues. I mean, like one issue is like, okay, you have come up with an estimator, and then generally any estimator that you come up, you need two things that a statistician interested. One is proving consistency, and maybe establishing the asymptotic distribution, because we want to carry out a test of hypothesis of confidence interval. So we need to see that whether you get a distribution which, or is it a kind of pivotal quantity in the limiting sense, so that you can carry out some inference, because after all, ultimate aim is to do the inference, or in this case, prediction maybe. So I would like to know that. So one advantage here is there is something called whitening by windowing principle, because there is a dependency among the observations. So how this dependency is going to play a role? Now, you know, your central limit theorem that is taught in the M.Sc class is assuming that your observations are independent. starting with IID, then in Feller-Lindbergh, we relax that condition and then we go into we relax that and then we say that, okay, IID-ness is not required, identicalness is not required, we will put appropriate condition on the mean sequence and variance sequence, and then you get the central limit theorem, right? That's what this is about. So here what we do is that when you are whitening this principle here, I have written in the beginning a estimator for the density, 1 by NH summation I equal to 1 k of. So I told you that you need to plus 1, and what actually happens, the kernel density estimator only uses observation in the interval x minus h and x plus h. Okay. So what will happen is that this will be, as h become, I mean, like, you know, this will become a small interval because h is chosen such a way that h is going to 0 and nh goes to infinity. That's how generally we choose. So this h is becoming smaller and smaller. What is happening is that this window is sort of getting independent with the other windows. So that's what this particular terminology, this terminology was introduced by Hart, and he called it as whitening by windowing principle. So you might have seen, those who have done the time series, you might have seen that the usual time series that we discuss are all of short memory, in the sense that if you look at the covariance function or correlation function, it's like exponentially decreases, most of them. If you don't have that, perhaps that belongs to a long memory time series, but most, because if it is long memory, the covariance sum to infinity. Otherwise, all of them actually converge, or you can see that the correlation actually. So for example, take AR. What is the correlation function? Phi to the power of h. And if you take phi less than 1, absolute of phi less than 1, that goes to 0, which means that actually the dependence gets, you know, relaxed or decreased as your lag increases. And that's actually the whole idea here. This is very important because when you start proving the dependence plays, when you start proving in the sense that when you propose an estimator and then try to investigate its properties, this problem you don't face in the IID case or in the independent case, but these are the extra things that you have to be careful. And in such a case, there is something called, so you need to see, anytime you handle dependent data, you prove consistency or normality, most of the time you have to come up with a control on their dependency. You have to control them. How do you control? There are various ways, like, you know, your Markov sequence, your martingale, all these are different ways of categorizing the dependence. And otherwise, there is something called, this might not have taught in an M.Sc class, what is called as mixing. So mixing is like, you know, you are taking an observation from, say, should I write it or if I say that? Okay, I think I can tell. You take an event belongs to a sigma field of, say, minus infinity to n, and another one from n plus k to infinity, and then consider P of A intersection B minus P of A into P of B, the supremum of all these sets. Now you can see that it is actually, this particular thing is a function of that difference k, alpha of k, and that actually goes to 0. Okay. So this idea is called the mixing sequence. So mixing is basically trying to have some kind of a control on the dependency. And when you prove the results relating to the normality and the consistency, we need to put conditions on this particular sequence alpha n. So most of the theorems are proved by making this kind of various mixing conditions. If you open Billingsley's book, you can find at least 6 or 7 different types of mixing conditions and their implications, etc. Those who are interested in the probability theory, they should look at that. So these are the main tools proving the for proving the asymptotic properties. So I start with a simple one. Let me tell you that I am not discussing all methods here, 1 or 2 methods just to motivate you. So you will see that, I mean the difference here. So let me consider a local conditional mean or local conditional median. So this is my, for the time being, I think instead of considering up to, I mean like all the past, I fix it. There are ways to choose P. That is a different problem. So right now I'll write like this. And if you denote yt like this and choose a delta n as a function of n, and then for any y, this y x1, x2, xp in this p-dimensional real line, you consider the number of i's such that they are, which is basically you are looking at the yi's, which yi's are there in this neighborhood, delta n neighborhood of that small y, and then fix which yi means I will get those index here. So, and if you count them, you will get how many numbers are there, right? And then take the average of them. Okay, so this is 1 by ny, I belongs to I and y. So this is called the local conditional mean. The local because I have now considered an epsilon, delta n neighborhood around that y. So this is, and if you instead of mean, if you take median, you will get the local conditional median. So this is what, and then Truong, I mean 1993, proved that it is consistent, normal, etc. Our Professor Patil has a paper with him because he also belongs to the same place, I think, North Carolina, Chapel Hill. At least he was there. Now I don't know. Is he still there or? Yeah. So he had a paper where for this kind of problem, they have addressed the problem through wavelets and then try to show that wavelet is another type of estimator, I mean class of functions, and using that you can actually construct estimators, and then proved certain properties related to that. And he found that this paper appeared in Annals of Institute of Statistical Mathematics, and he proved that the wavelet based estimator, in fact the methodology is applicable to regression as well as auto regression, and for functions with possible, in fact even if you have discontinuities, kernel method will not work well, whereas wavelet take care of that, and that's what he has found in this particular paper. And of course there are a couple of other things, MISC, etc., all those things derived. But the main thing about the paper is this. So this is one way. Another way is like what is parallel to the Nadaraya-Watson estimator in the case of independent setup. So I already discussed that it is there. Oh, I erased that, the one which I wrote there. So what is the parallel to that in the case of dependent case? So the parallel to that in the case of dependent case, you can actually consider like this with product kernel. So you look at this kind of a setup, and then this, consider this, and then people have investigated. Mainly this started with Robinson, and several people have contributed to that, and then investigated how this works. I mean, what is its property, under what condition you get consistency, etc. So this is where basically when you have, see, all these need separate investigation because you have dependent observation. So you are in time series setup, so you need to have this particular one. So this is about non-parametric kernel regression. So that's what, so it basically the same thing which I wrote there. And then the next one, which is I have a lot of interest, what is called local polynomial regression. Now I'll tell you this idea of this local polynomial. See, let us keep the local polynomial aside. If you have a very straight line function or a straight function, then stress approximation theorem. That's one of the important results. Your entire time series box, actually Jenkins method is hanging on that. So any continuous function can be approximated by a polynomial. Okay, so I can approximate a polynomial. So what I will do is that in this case I take a, because then you are much more better stand, because I am not insisting on linear. So let the function be any type. I can in the local interval, even if it has got zigzagging behavior, I can use a polynomial there, and then you get better approximation. And that's the basic idea of local polynomial regression. So what is being done is the function that you have is actually approximated. So a polynomial of specified degree are fitted locally in the neighborhood of a given argument of f. Well, you should look at, there is a book by Fan and Giebel. If you are interested, its title itself, Local Polynomial Regression. By the way, Fan has a lot of couple of papers with our Professor Patil also. So he has worked with Fan. So what is being done here is you are approximating effects with this, where this beta j are basically derivative, like the derivative of the function. So you get this is beta j is local parameter. It is called as local parameters, and then you try to approximate it. And here the local polynomial. So what is being done is like you minimize this quantity with weight of this kernel function, and actually what you can see that if you put p equal to 0, this actually reduces to Raya-Watson estimator. That's what. So now, oh sorry, I think where am I? Going forward. Yeah, here. Okay, now in time series, so I think what I have 2-3 methods which I have shown, basically trying to estimate the conditional mean or the mean function, not mean as such, the mean function f, right, using this method. And this is basically the non-parametric way of estimating, because we never had the parameterization in that. So this is, and now another important issue here is, so those conditional means basically I was talking about xt given x1, xt minus 1, xt minus 2, etc. Now, for example, our Dr. Manik, he is an integer time series man. He would like to predict given x1, x2, xt, you want to say xt plus k. So he may be interested in the conditional distribution of xt plus k given x1, x2, etc., xt in a discrete setup. So what I am trying to say that, so beyond one step, suppose we want to have the prediction. We know that in the case of, if you are in a time series class, you know that in the ARMA or ARIMA case, how this is done. This is done in a recursive manner. What I will do, using xt, I will first predict xt plus 1. And because it is linear, the conditional expectation goes through nicely. Isn't it? Because that's a property of the expectation. So you can predict xt plus 1. And once you have xt plus 1 predictor, I will now predict xt plus 2 using this. Same idea we are going to apply it here in this case. So what we do is that we will actually have this formula written like this, and this is, we'll consider, so for t plus 1, I will actually consider the next one over here, the next one predicted over here. Replace this with that f hat of that quantity. Okay, and continue like this. So next one you have to have the next one, whatever that you obtain. So that's how this is predicted. So this is called non-parametric multi-step prediction, right? Well, another problem in which I just now mentioned, that when I started writing that, for the time being, let us take p. How you determine the order of the p? I mean, what p should be taken? Should I take 1, 2, 3, etc.? So we all know that in time series class we say that, okay, you can look at the correlations, autocorrelation, partial autocorrelations. You can look at AIC, BIC, etc. All those things will help you. So what is the non-parametric? Because those, all the information criteria uses the likelihood, and it is parametric. So if I really want to have a non-parametric way, what is the way to do that? So order determination can be done. You consider the estimated FPE non-parametric way, and there is a paper by, this is quite lengthy, so I am not including that here. So those who are interested, you should look at this paper. How you can get in a non-parametric way, how you can, see, AR order is determined by using FPE, final prediction error. So what is the non-parametric version of that? So that's what this paper is talking about. Now what happens that in a recent, data science, people are interested more on more complex model, because the kind of non-linearity is much more worse than what we thought. So people start, your usual generalized linear models are not enough. Linear models are not enough. Generalized linear models are also not enough. So we go for further extension of that, what is called generalized GAM, generalized additive model. And there is a book by Tipshirani, If you have not seen that, please look into that. Generalized additive model. So what is the parallel of that in the context of time series? So the parallel of that in the context of time series is given by this nonlinear additive autoregression model, where you have these functions, and we need to estimate these functions, all of them actually. So generally this is done by in data science, what they call it as backfitting algorithm. And backfitting algorithm is assuming that this is true, you take one of them and minimize, consider this. So here what can be done is that in such a case, you can consider this as the response, this as the predictor, and then you can get one of them estimated in a non-parametric way. So you have developed a regression. Now you need to do for all of them, because this is one of them, and then you need to get all of them in such a case, and that's what, so iterate until the convergence, highly computer intensive, and that's what your backfitting algorithm which is being used in the generalized additive case with time series structure. So iterate until convergence. In fact, when you are in a time series setup, the convergence and other things are very slow. It takes time. Those who are interested, they should look at this particular chain and say. And then independent case, there is a book, very interesting book, Generalized Additive Model by Tipshirani and his group, ST Tipshirani and yeah. So now here that is what is actually, so this is the problem. Like here, sorry, I may assume, I may have to bring conditions. Right now I have not written those conditions. Here basically I have assumed that you simply say that this model is correct, and then try to estimate this particular one using this conditional, treating this as the response. So I can write this in this particular fashion and then use the backfitting algorithm. This is a general algorithm. There are various versions, various papers, etc. I am just giving the first paper in which this appeared. Now you see this is almost 20 years before. So you can see that how much changes might have come. Since I am not working in this area, I don't have much of things, references, the recent one, but of course one can actually look into that and then do. Now, okay, now my interest is the next thing which I wrote there. You can have this particular one, this sigma xt minus 1, which is called as the volatility function. So mean, at least 3-4 methods I have mentioned. Now I would like to estimate the conditional variance, sigma xt minus 1, in a non-parametric way. So how do you go about that? So one way is so I have formulated that here. Xt is this plus this. So how to account for volatility? And so volatility is the means conditional variance. So parametric model is the one which Professor Madhavarao was talking about, Arch-Garch, Angel Bullerslev, who got Nobel Prize for this. So that's pretty simple. It's like you consider for the variance a model which involves the error squares, because error squares expectation is sigma square. So you consider the error squares present and past, and then consider a model for sigma square. See, the problem is that we cannot have a model for sigma square directly which involves t. Unconditional is not possible, because then it becomes non-stationary. So they try to see that what is the way the conditional variance can be brought in, so that you can now account for the changes in the conditional variance, and that's what the Arch-Garch is. But the Arch-Garch is actually a parametric model, in the sense that you have the parameters sitting over there, and then you can, it's like alpha 1 epsilon t minus 1 square plus alpha 2 epsilon t minus 2 square. So you need to estimate alpha 1, alpha 2, etc. So instead of that, if you consider that as a function, a variance function, then how you can estimate. So that is what the sigma here, or what I have written here. So you estimate this quantity. So the conditional variance at time t given the previous time period. So this can be estimated. Now there are some work in the literature. There are quite a few of them. So you can also see this in this setup. One such, this is a kind of local linear kind of a thing, estimation, where you are estimating this as well as this, So this particular minimization gives you this parameter, and then this gives you this parameter. So you can actually see that this turns out to be the estimator for the variance. This turns out to be the estimator for the mean, conditional mean and conditional variances. And yeah, so this is a simple non-parametric volatility model. This is non-parametric because I haven't really said E of expected value of this mu yt minus 1 is alpha plus beta yt minus 1. I am not saying. It is simply a function of the past. And then you estimate what is that function directly. Okay, what is that function directly? Well, there is an issue here. I am representing all it with just one lag. Of course, if it is a multi-function, you may have to consider it with that many arguments. So it will become more complex. Choice of k actually in a density estimation, it is not. It won't really matter. I mean, it matters, but not to the extent of. So that is where okay. Since he asked that question, one of the problems there, if I computed MISC, that mean integrated square error, so you try to minimize and see that for what k this get minimized, and that is called as the optimal kernel. And if you have read something, you might have heard this word, Ipanechnikov kernel. I don't know how many of you have heard. Yeah, so which is basically trying to minimize the MISC and then try to see that what is that gives you. So actually, when you do the practical, of course, more than me, Professor Patil can say that bandwidth is more important than the choice of the kernel. Bandwidth can, even small changes can make a lot of problems over there. But kernel, because there are certain properties, we are that class of kernels, we are trying to fix it in the beginning, which has certain properties. So there are a lot of functions which are already of the similar type. So we don't even really say that this is particular one, because that is enough to talk about further calculation. Like, you know, you get mean of that is 0, a symmetric function, and then bounded. So that there are a lot of functions. So all of them gives you more or less similar kind of thing. Yeah, sure. So this is one way, and then the next way is what we have actually done is like there is another paper where this is okay. This is the just asymptotic properties. I think this is already there. I think I am skipping this. Now what has happened that, okay, let me now try to just give you some kind of thing what I am supposed to discuss now. So if you have a kind of a arch model where these parameters are there, what happens that many a time the variation cannot be accommodated with this finite structure. So instead of the alpha, beta, gamma, these coefficients, what we thought that you can treat them as functions of time, but fixed. Functions of time, but fixed, and then estimate those functions. Right? So that's what actually there is some paper which I think this is appeared in Annals by this Delhaus and Rao. This Rao is Suhasini Subbarao, that's Subbarao's daughter. Subbarao was a time series person, and this Professor Patil may be knowing very well because he works in wavelets, price glaving, right? Okay. So what we do, consider that in this context, if you have a Garch type of model with coefficients as time varying, then how that can be estimated. So what we did was like, so this is the model. This is called typical arch model. Of course, you have only parameters here, but I made it as functions of time now, so that it can be more flexible. And you can write the similar kind of a thing for Garch also, and then try to estimate these functions, and that's what we try to do. So yeah, so we call it as time varying Garch, and then estimate these functions, this omega, alpha and beta, estimate them. Well, this is slightly different from the approach that I mentioned, sigma square y. I am not estimating sigma square y directly, but at the same time my parameterization is slightly different as opposed to the earlier one, because earlier one you have real parameters, here you have functions. Well, this is what this whole thing about. I think there are a couple of theorems and other things. I just want to show you a data analysis, and then that should be the end of it. Yeah, yeah. So here we have done couple of different data sets, and then we try to see that what is the aggregate mean square error of this particular prediction. I mean that you have making, and error of monthly realized volatility forecast. So you have done the volatility forecast and then try to see that how the mean square error behaves. So we see that these models, these expansions stand for simple Garth, exponential Garth. This is like what Jagannathan. Garth means fractional integrated Garth, time varying R. This is Suhasini Subbarao, and then this is what we try. And then we see that in most of the cases we have less prediction sum of squares. The aggregated mean square errors, monthly realized volatilities are less in all these cases, and it actually captured the behavior. And this is done using I just want to show you the picture. It's actually when you forecast, it captures that troughs and peaks correctly. Yeah. So it's actually this should be a color graph. So then two different colors. Unfortunately, I don't have it here. So it actually matches well. This paper has published. So if you are interested, you can look at that. It appeared in Journal of Nonparametric Statistics. So what methodology that we used, because these are we used local polynomial estimation for this, which is basically described in. I think that's a better time to stop. So what is the moral of the story? The mean function, conditional mean function and conditional variance, instead of parameterizing them, you can estimate them by as a function and then study them. There are difficulties in terms of proving the results, but certain assumptions like mixing and other things will help you to get the asymptotic results proved. As a method of estimation, you can actually apply one of the methods that we discussed, or there are several methods which I have not discussed. One can look into that. Generalization to more general functions that one can make, generalized additive model, which are these days very popular, because generalized additive model capture the non-linearity in a much better way as compared to the usual. I think with that I would like to stop. So if you have any kind of difficulties or want to ask something, if you cannot ask now, you can shoot a mail. I will reply to you. ram@unitunion.ac. Thank you. Okay, thank you.
I have a query.
Ah.
You showed all those computations, So what was the software used
R.
for those computations?
R.
You needed to do coding or already?
This is actually one of our students did the coding. I mean, like I am not that expert to do all the coding. So we have some students. Yeah, but he also stopped doing all these things now. Yeah, because nowadays, oh yeah, okay, now for the young researchers, I want to tell you one more thing. See, when we were doing PhD or maybe off late a couple of years, there is no concept of reproducible research. And nowadays, every research is actually reproducible. So when you write any program or use any data, every journal is asking you, give a link to that, the data, or give your codes, we will put in the supplementary material. So this is becoming mandatory because the concept of reproducible, earlier research, many of them were not reproducible. People claim lot of results, but there is no way to verify. But nowadays things are getting changed because of the computational advancement. So you should know that reproducible research is something very important these days. So write programs, so, make it user friendly, and then submit to the journal when you are submitting a paper. That will help you. Many people are making R libraries also, which is also considered as an important activity. No, it did not make it as a library, no. We just submitted the paper and then they asked the codes, we gave them. A professional developing, it requires little more knowledge. Not all students cannot do that. Yeah. Right. Yes. Yeah. Right. Yes. Any R developed programming, which is all not there, and if you have developed that, you get a recognition, because R also has a journal which publishes that document if it is not done earlier, and it will be a part of the R system. So that is, some people are doing that. Thank you. Go then. Oh, ಹೇಗೆ?
On the organizing part, let me thanks to Ramanathan sir and Madhurao sir for chairing the session. We have the few announcements. We have the two things together. We have the tea break, and before that we have the group photo. So I request you all to assemble at outside this hall. We'll have the group photo and tea break, and we'll come after sir for panel discussion after 15 minutes. Yes, see you. Yes. Good evening. So we'll start the panel discussion. We have Professor D.T. Shirke sir, who is the chairman for this panel discussion, and Prakash Patil sir, K.S. Madhavrao, and Professor T.V. Ramanathan sir. The topic for the panel discussion is the way forward in non-parametric statistical methods. So I think we'll start the panel discussion. Yes, sir.
So good afternoon to all of you. They are asking me to chair the session, that's why I have taken initiative. Otherwise, I would have been happy to respond some of the questions. Now, this session is more or less is focused towards the students' queries. Of course, we invite few questions from students also. We already have collected some questions from experts, and we would also talk on that. Experts will elaborate on those questions. But one of the panelists suggested we should focus students. My experience says that students usually doesn't have questions. So you can say this is a hypothesis. So if you really want to reject the hypothesis, I give you an opportunity to ask questions. So you can start, we can start with some students, okay? And students, I think the population is quite rich. Students means a research scholar also. I should not say that the teachers are also students. Actually they are, but for this discussion, we should not treat them as the students. So master students and PhD scholars and active researchers, they can raise some questions. Maybe 4 to 5 questions we can take, and then we can go for the questions already enlisted over here. My suggestion would be the question preferably should be related to non-parametric, but it's open because the 3 panelists, they don't only work in the non-parametrics, they are basically experts and eminent scholars in statistics. So if you have a question outside that, that is also welcome, but let us not deviate much from the theme. So should we start? Yeah, so.
Can I just start?
Please.
Yeah. I think Professor Shirke has kick-started this panel discussion with the right kind of introduction. So I was suggesting to him that we should focus on the concerns or the queries or the way forward by keeping our young students in mind. And as you all know, we are here attending a symposium on non-parametric inference. So my young students, you obviously had few topics related to non-parametrics in undergraduate program and again in master's program. So you have a certain amount of clarity on the topic, and you have heard us this morning some of the areas where non-parametric inference has really made an impact, not only on the researcher but also on the practitioners as well as the end users. So with this background, I would appreciate if the students can relate their questions to non-parametrics inference as much as possible, and Professor Shirke has also made that point very clear. That doesn't, I mean, that should not limit you to ask other academic questions, and probably you can prioritize them, then that may come later on. And let's not unnecessarily waste our time by talking about the career opportunities and all those things. This is not the right forum to raise all those issues. Of course, they are all important. Maybe your professors will definitely guide you in all those aspects, maybe after the conference or maybe sometime down the line. So probably I thought I would add these remarks along with the Professor Shirke's remarks so that we can have a right kind of questions, be free, and language should not be the barrier. So there are good people who can translate your question into it should not be a barrier.
You
Then
can speak in
Marathi, and definitely we all have a little, I have little understanding of Marathi. If I don't get the question correctly, so there are people who can help me out on that. Yeah. Thank you.
हे सुद्धा सांगतो की मराठीत प्रश्न विचारला तर चालेल असं सरांनी सांगितलं. मला कळतं ना की सर्वात मोठी अडचण काय असू शकणार आहे. चला. Experts should not recommend that we should start a course on communication skill, thinking that you don't have a way or you don't have that particular skill. Okay? तर बोला, चुकीचं असेल तरी सुद्धा बोला, कारण हा जो काही हा आजच्या कॉन्फरन्समधला हा भाग जो आहे तो विद्यार्थ्यांकरता आहे, त्यामुळे विद्यार्थ्यांनी बोलणं आवश्यक आहे. त्यासाठी टाळ्या वाजवा एकदा, तो पहिल्यांदा बोलला.
Hello sir, I am Sumit Zogle from M.Sc. Applied Statistics and Informatics. Question to Madhavrao sir. In stock market analysis, we use MACD estimator. In that indicator, we use exponential moving average. So that indicator has two lines. One line has 12 period lines, and another is a 26 period line. And difference between 12 period and 26 period, it's some patterns happen, compression and diffraction. So how this exponential moving average usually in MACD indicator?
MACD indicator. This is talking about some measure that they use in
moving average, compression, diffraction.
Ramanathan? Yeah, his topic.
Yeah.
I have PPT, so I show. In stock market intraday analysis, you use MACD indicator for buying and selling. So in that indicator, we use exponential moving average. So in that indicator, there are two lines, green line and red lines. One line has 12 exponential period and second line has 26 exponential period. So there is a difference between two line is an indicator. So if two line compress and compression of depression, we take decision of that. So how exponential moving average work in that scenario?
Actually, I didn't understand correctly what is that MACD thing because I am not very familiar with that. But I'll tell you what is the whole the gist of it. Basically, a moving average is actually a smoothing. Okay, because when you compute moving average, we are giving weights to the observations and taking a so any data which has a dependence on the time. What happened that if you simply consider in a IID situation, you can go for a full average, so it reduced to one number. Now what happened that time plays a role. So I don't want to have a one number because I know that it actually changes. So I want to know how the change is. So that's why the moving average works. So moving average is ideally a smoothing thing. Now the question here is, what is the difference between the, like exponential moving average, the usual moving average?
moving average take only a finite number of observations like 3 or 5 or 15 at a time and take the average of them and then move that and then take the next, not next, leave one out and then they'll take the next one like that. Now, what is happening is that towards the end or towards the beginning, all other observations are not being used when you actually compute the average. For example, a 3-point moving average, you take only 3 at a time. So next, suppose there are 25 observations, another 22 are not being used, and they may have a role to play also. Now, in exponential moving average, it is such that you are basically trying to compute what has happened in the past, in the entire past, wherever the information is available. So it is like, you are computing it, the whole of the past is being used to get the next one. So this smoother, this particular smoothing which we use is having that peculiarity because, and how do you give this alpha value? It is based on like, if there is too much of volatility or too much of variation, I should give lot of importance to the previous values, which means that the exponential moving average is like alpha yt plus 1 minus alpha st minus 1. So it's like alpha, which value of alpha I should give? St minus 1 is the moving average of all the time observation at the time point t minus 1. Okay. Now this is what called the exponential moving average. Now how this is used for this MECD, I really don't know unless I look into some document. But the whole of moving average is basically trying to use all the past and then replace it with, so it's like gives you a trend, how the trend behaves in a smooth version. Okay, if anybody want to add to that, Oh, intraday thing is, that I know. Intraday thing is basically, in a stock market data, you only get closing prices or opening prices or hourly prices. Now, intraday data is basically, it's a high frequency data in the sense that every trade is being recorded. So, for example, if you consider 24-hour clock in NSE, National Stock Exchange, which is completely automated, you can actually see that in a 24 hours clock, how many trades are happened for the Reliance stock, for example. So it will give you the data like, what is the asking price, what is the selling price, and what is the volume. All these details are available, and this is called basically some term tick-tick data or high-frequency data. Now the advantage is that when you are given one observation per day, you don't know the variability of that observation because some people want to invest in the morning and get the money back in the evening. So I can't do that because I know only one observation or two observations per day. So you would like to know what is the way the market behaves, and this will be captured in the intraday. So exponential moving average can do that. Don't take your particular thing, which I don't know really. But otherwise, this is what is.
Let me add you something. Slightly different take on this one. First, little following on his, yes, exponential moving average is, exponential average, the moving average is basically taking, assuming that a very, very, very old observation also have an effect on your tomorrow's thing, that's why use exponential. But other way to look at it, actually he mentioned one of the name, Gisbel, the author.
Yeah.
She has a paper in which she showed that actually exponential average is also a kernel smoothing, what he talked about. So, not to answer your question, but if you want to understand what Professor Ramanathan talked about kernel smoothing, there is another way to connect your exponential smoothing to the smoothing he talked about.
I think you must be using some software, right? The strategy that software recommends. Basically, mobile app must be recommended by something like a money control or so and so forth. There are Zerodha, so many things are there, and their strategies are different. So you will have to go for what kind of strategy they are adopting to recommend whether to buy or whether to sell, right? Within a day, intraday, within a day, right? Yes. So unless otherwise you have that kind of component, it is very difficult to explore or even say something on that. Don't know. They may not be using every, I should say, generic reference to do that particular thing.
Just I want to add one more thing. In quality control, your PWMA chart, it's basically the main fundamental thing is same.
So, Malik sir, maybe, actually, exponential moving average is a kind of, it's a kind of infinite auto-regression. Not infinite, up to whatever observation that you have. Because you are basically trying to find the previous one, the current one with all the previous one smooth. That is what it is.
A very interesting question. I would recommend to take up this as a project for your second year. Right? Because it seems to be you are very familiar with that particular domain, so you will find it very interesting when you deal with that.
Yeah.
Where the weights are exponentially decreasing towards the past. Should we go for second question? Yeah.
As sir has told that the pivotal trading system, how does it affect the market and the sentiments of the market? I want to ask to Madhav. You have told about the pivotal system. Right? What are the advantages and how can it affect the market sentiments?
Yeah, I told you, there are so many factors which affect the sentiments, right? See, for example, if somebody is declaring the dividend, let's say one company is declaring the dividend, so obviously that will have a positive impact, right? Isn't it? And let's say very close to June, every year most of the companies declare their results, right? So if somebody is making a loss, heavy loss, obviously that will bring down the pivotal quantity, right? So there are technical factors which are related to the performance of the company, which will have an impact on these the indicators, the market sentiment indicators. Also, there are some issues which are related to the non-performing assets of the company or issues not related to the company. See, for example, some of the political decisions, some of the economic decisions that the government makes, it can also impact the stock market very adversely. Even some of the rare events like let's say famine or maybe earthquake. So these are some of the events which also can affect, right? Recently you have seen in areas which are prone to terrorism, even one incident of terrorism has brought down tremendous the stock market tremendously down. So these are both company related issues, what we call as the performance indicators of a company, and also there are so many other mundane affairs which also affect the sentiments of the market. So have I answered your question? Yeah.
Yes, sir.
Good evening, everyone. My question is regarding continuing of his question, because I have an interesting scenario. I was analyzing Wipro stock, and it was about quarter. It was going to give quarter result, but stock has been falling since 2 weeks, and after revealing their quarter result, the results were terrible, and it should fall more as ideal guess, but it went up. I think it's all about, it's not about price, it's all about short and long positions. So my question is, instead of analyzing price and volatility, can we analyze open interest in the same way?
Can you analyze?
Open interest. Derivatives, I'm talking about derivatives trading.
Huh?
Derivative market. Can I explain what is open interest? If you sell me one
price, of course, we don't directly analyze price, we always analyze return.
The reason being that automatically there is a variance stabilization and automatically there is a tendency to become normal is done in the case of return, because you are transforming PT, log PT upon PT minus 1, which gives you the RT, which is the return. So the thing is that when you have any data which actually you cut down to pieces and then look the discrete version of it, some loss of information is bound to happen. Like, I'll give a simple example. In the entire real line, I say that if it is less than 0, it is plus 0, and if it is greater than 0, it is 1. Now what happens that the binary 0, 1, I'm covering the whole real line, but I have only two outputs, 0 and 1. What do you think the information from this data as compared to the entire real line? This information will be always less, and that's what happened with many of the discrete setup. So if you try to, now derivative, if it is a one-to-one thing, like, so in many cases I think the derivatives are being analyzed, the price of the options are being analyzed. Only thing is that this is, when you do that, it is basically directly relating to the, not the stock. Now it is already a transformed quantity. I mean, like, derivative is actually a derived quantity from that. So whatever that you are predicting is, this derivation is like, it depends. Like what way, for example, I mean, like, what is an option? Option is actually because you wanted to have a security on the risk is to be supported on that particular stock or whatever, and that is why an option is put. Different types of option, whatever it is. Okay. So when you consider option price may be behaving in a different way as opposed to the price of the stock. The reason being that the option price is trying to cover the risk, whereas if I am more towards, able to sort of withstand my risk, I would actually don't go for option, I will directly go for stock. But at the same time, the stock is actually dangerous because I may lose, everything will be lost, whereas in option, at least there is some security on that. So derived quantities, option, futures, everything, it has its own limitation, but one can analyze that, but you will get only the answer to that, not to the stock of the, directly on the stock price. That's what my feeling is.
Yes, but I think most of the time derivatives price also derive the underlying asset, because India is largest derivative market, as you know. So I think volume and volatility in a derivative is much higher than underlying asset.
True.
So
it's possible. This is what we do in the, your Black-Scholes formula, what we try to do.
Exactly.
We do the same thing. You have the volatility. Volatility is, so if sigma is to be computed in a BSW formula, then I will be doing that actually using, how to get this. So I go for the price and estimate the volatility and then put it in the Black-Scholes formula to get the price of the option. That's what we do. So actually you are using it, but what is happening, the instrument is a derived quantity. Yes. So my point is, once it is derived, it has certain purpose and it covers certain things. Whereas price is directly affecting the market. It may have its own way. So what my feeling is that you can't compare directly both the things, because it has got some definition. See, this is like X and GX. Now when you transfer them, it's some property is lost, some new properties will definitely come. So is it a one-to-one? It may not be one-to-one. So that is why what I am saying is that, so options you can't directly compare to the prices. Whereas there are situations it may be same also. That depends on the stock, the market. There are several things, because in this particular thing, you consider the time period, lead time, so several things. When you actually worry about the price of an option. So all these factors are embedded into the the derivative, whereas price is not affected by that. Price is affected by the volatility of the market directly.
There are some conditions where, in my example, Wipro has been falling from last 2 weeks before posting their quarter result. It means some people know about the quarter results.
See, one thing you should understand, that we cannot swallow the transparent. There are people can determine the market. There are people can change the direction of the market.
Yes.
To a certain extent. You might have known that person who what is his name?
Harshad Mehta.
Harshad Mehta. Of course, there are several Harshad Mehtas, but they are not coming out. Their names are not coming out. That's all. but he unfortunately named. So what I'm trying to say that market is not a completely free kind of a
Yes,
thing where
yes.
everything is. There are several things, several players who can actually change the thing. So even the data when we analyze, we only, I won't take it in the complete spirit of that. So there may be factors affecting to that. We have to have a caution. I mean, like.
I think I really appreciate your interest in stock market. And my recommendation to Professor Mahadik to introduce a paper from actuarial science. I do not know the code of that paper. It could be a CT1 or CT4, financial mathematics. So we can offer that particular course as an optional paper to the students, so that those who are interested in that particular domain can go for that particular paper. And of course, you should have experts like Dipesh Bhatti. Maybe some online lectures can be scheduled from University of Rajasthan, where he had already delivered a series of lectures to our students, and he is the right person to do that. Okay. I really appreciate, and I would like to say that let us close down the session on the stock market and switch to some other domain, so that the rest of the students can also some questions.
Thank you.
Thank you. विद्यार्थ्यांनी प्रश्न विचारतात खूप असं म्हणतात लोक, आणि आज एकही विद्यार्थिनीने प्रश्न विचारलेला नाही आहे.
No question of asking any question.
Very basic question. I think everyone knows answer also. That's all non-parametric test. We know all about the non-parametric test. So, if we consider sign test, in the statistics we use the combination of all signs. This is statistic, or the mean of the sum of all signs. Then this statistic follows binomial. Okay. And the same, the next test is Wilcoxon sign rank. And what we do in the statistics, it is a combination of sign also rank. Okay. So my question is that this sign rank based statistics follow which degree or no, but do not understand it. The distribution of statistic of Wilcoxon sign rank.
Which cannot be written in the closed form, like your science statistic. Okay, as you rightly said, science statistic follows the binomial distribution, but most of the other non-parametric tests, they don't have a distribution which is identifiable with any of the distribution that you studied in your undergraduate or postgraduate courses. But having said that, your successive probabilities can be generated by use a nice recursive formula. Okay, so using that recursive formula for different values of n, there are standard table values. People belonging to my generation, we used to refer to those table values and solve our problem. But people belonging to your generation, so you can get it with a single a click of the mouse using that software. So it will provide you that's all the cutoff points with a single click. Yeah. You don't have a closed form representation. Correct. Yeah, that is for most of the distributions. Very rarely you get a closed form distribution. Okay. But as you rightly said, asymptotically all of them will have normal distribution. Okay? Yeah. Especially in the one parameter case or one sample problem, all of them will have normal distribution asymptotically.
See, just I wanted to add one thing. The whole idea of non-parametric is we have more number of unknown distributions than what we know. We know only very few. You give me any function which is non-negative, I can give you a distribution immediately if it is integrable. You give me a function which is integrable, non-negative, I will give you a distribution to you. Okay, you integrate and whatever number you get divided by that, that is a distribution density, isn't it? Non-negative. So that what name that you are going to give? Similarly, you take any combination of discrete numbers and then you consider them divide by common divisor such that the sum add to 1. That's a distribution. So this is why, I mean, the distribution basically characterized by some properties. So not every member in that we cannot give. Some of the people we know, normal, beta, this, gamma and all. But there are several unknown things. So this is one distribution like, okay, it is a distribution. It has those properties. So, you know, it has connection to today's, the whole theme of the symposium also.
Hello sir, good evening. To the comment of Ramnathan sir. Actually, we have taught to deal with parametric data in bachelor's as well as in master's as well. But if we consider the field of non-parametric, it is like a C. So what I think, or what I need guidance regarding the fact that if we get a particular data, we first try to see whether it follows a normality. Actually, we wish for that. It should follow normality. But if it not follow formality, so what should be the procedure or what should be the approach to deal that kind of data to get some the results that we are looking for?
Okay, so it depends on what you want to do. See, for example, I'll give a very simple example situation. I have a symmetric, nice picture distribution and I want to do inference on population mean. What is the best thing that comes to my mind? Sample mean. Okay. Now what happens that I realize that, oh, no, this distribution is skewed and it has some problems. It has tails. And then I really then realized that I did not do any testing, goodness of it. I started realizing that this normal is out of consideration. Or I should, not only normal, I don't want to now deal with the mean. Rather, I would like to deal with the median. So, so it's like certain things tells you that, okay, you need to deviate from what you are. And if you have this kind of a thing, later, I mean, median is of course a special case of any quantile. So, I mean, like I can even go for any quantile. So that is why in regression, you are considering the mean, isn't it? Expected value of y given x is, expectation is the mean. What is the guarantee that, I mean, like if you have a very, curved kind of, suppose the mean doesn't exist, what you will do? So that is where we are interested in, I mean, like instead of mean regression, I will go for quantile regression or median regression. I think somebody was
yes.
talking on median today, no? Somebody was, no. So what I am trying to say that situation, what question that we are answering, I mean, what question that we need to answer, tell us that how far deviation. So easy things can be done, then I will do the easy things if that solve the purpose. But if that doesn't serve the purpose because I am unable to justify, then I go more detail, I mean, more complex things, or I start asking the questions in more complex way. So when do you deviate from mean to median or median to quantile? Because it gives me, the data tells me that, no, this doesn't have a kind of, nice picture in terms of existence, tails. So mean is actually not a good measure for the central tendency in this case. So then naturally I should, so question, depending on the question, I mean, what you want to answer. If it is simply a model fitting, well, you go away, I mean, like you can start by looking at the histogram or fixing the density and see that what is the kind of picture it is matching with any of the standard distribution that you know by name.
Yeah.
And then try to see where you can fit it. I mean, and then you can do a parametric inference to that. And there are class of distributions, like there are sometimes what happens that not just one distribution with certain good properties. Like for example, there is a distribution called generalized hyperbolic distribution, which has 5 parameters. Like normal has 2 parameters, mean and variance. This has got 5 parameters: location, scale, shape, skewness, kurtosis, which means that several type of variations can be accommodated under that. Normal is a special case of that. So if I start feeling that the data has this kind of deviation, then I will go according to that. So it's not the question of fixing that distribution in advance and then doing that. Depending on what question that you want to answer. I think anybody want to add to that?
I think I'll say something. Okay. I know your question is general. Have a data, how to analyze, what to fit, right? So first thing I would do is, I might be biased because I do non-parametrics, but first thing I'll fit a non-parametric curve. Just like he explained, you get a kernel and find those functions together, add them and get a curve. And based on that one, I'll see, oh, does it look like something I know? Whether does it look like a beta or gamma or normal? If that fits, that's fine. I'll do whatever answer I have to do, see whether that explain the thing that I want to explain. Good. The next thing I do is, okay, go back to your non-parametric curve again. Keep changing the bandwidth, see how it looks like. Because even if you think that you have a normal and you got this thing, but this still, when you went to answer the question, something still remains unanswered, unexplained. That time you have to go back and see your non-parametric curve one more time. Change the bandwidth small to big, trial and error. And occasionally you might find fault. That is, you have a normal distribution pretty much everywhere, but there could be some of the high oscillation in the density functions. And those may not get picked by us being normal, and that may not explain, or that might lead your answer not explaining what exactly happened. Therefore, now in this case, you have to understand that beyond normal, even though there's much more sophisticated inference you got to do, and then you are left with non-parametric procedures. And of course, there's slight disadvantage is that you need bit more sample, or whatever inference you have will have slightly less confidence interval or whatever it is. Those would be there. Okay. Same thing, whatever I said about the density function, same applies to regression as well. You can assume, you can simply estimate non-parametrically, right? Or then looks like a quadratic, cubic, whatever it is, fit that one. If everything explains, no worries. If it doesn't explain, try playing with it. See what else extra things are there.
It's like trial error.
Trial, and then and moreover, even if your standard model fits and get your answer, try other procedure. Try non-parametric. Try even some other whatever procedure you know. Try that one and see whether those all 2-3 different answer lead to 2-3 different procedures lead to the similar kind of answer, same ballpark or not, and then you form your final decision or inference based on that one. You don't go by simply parametric, non-parametric or algorithmic. You do all the things. Okay? That's the approach one should follow.
So you should have the box anecdote in your mind. All models are wrong, but some are useful.
So thank you, sir.
To recommend one book, perhaps the experts will agree with me. There is a term which is called as EDA, Exploratory Data Analysis, and there is a nice, wonderful book, must be in our library, by John Tuckey, 1973. So basically you have to start with histogram and then proceed further.
Yeah. Thank you.
The one thing I want to add to your question, Fisher has answered this question in 1930s. So if your data is not normal, if you still continue to work in the parametric inference framework, you should go for a transformation of your variables, right? You have learnt about that in your master's program.
Log transformation.
Arcsine and log transformation, square root transformations. So if you wish to continue in the framework of parametric inference, that is the right thing to do. Yeah, box Jenkins transformation, all those things you can do depending on which is the area that you are working with.
Okay, thank you.
Good question.
Hello, sir. Good evening. Myself Kalange. I'm working as a teacher in one of the affiliated college. I want to ask two questions. First question is, when we think about parametric testing of hypothesis, we propose a test statistics, and all we know or all we need is the distribution of test statistics under H0. If we get it, then we are all through. That is the situation. In non-parametric inference, I neither studied it well or not taught in a classes in undergraduate. So if I get a statistics, then how to find the cutoff points and like that means in testing of hypotheses, as it is expected to throw some light on non-parametric testing of hypotheses. I think little have been said about that. Just throw more light on that. Second question is related to the in parametric inference, most of the time we talk about the mean. In non-parametric inference, we talk about median and quartiles. These are the positional averages. And we know these two measures. Among them, mean is said to be robust one. It has more merits as compared to other one. So can we say the inference based on parametric methods is superior than inference based on non-parametric inferences? Thank you, sir.
Can I take up the last question? Yeah. The answer to last question is very, very simple. So thank you for asking a simple question. If your parametric assumptions are right, the parametric methods are wonderful. And your assumptions are wrong, it's useless. That's a simple answer to the question. There is nothing more, nothing less. But going to I might say about something of fourth question as well. Okay, about the first question. About the first question, actually, I don't want to go too long on that one. There are a couple of procedures on that. You have a test statistics, which is completely, first thing, you don't, sometimes you need to know all mathematics and things, and that's fine. But occasionally, even if you don't want to bring those into practice, that's fine. You have a test statistics, looks very complicated. How you want to find asymptotic distribution? You tried U statistics, tried every asymptotic theory. Oh, leave that one aside. There is a simple procedure called bootstrap. Just keep repeating the sample, find the statistics hundreds of times, plot the histogram, you got a distribution, and use that one to test the hypothesis. Okay, to find the cutoff points. That's the one approach. And second one is permutation test. Do they have permutation test? You can read on permutation test. So you can permit that thing and see what different kind of things get, and there's another way to find cutoff points. Does that make sense? Sorry, I'm giving it because the person is asking the question. That's why I'm not going to go to minor details. I think you probably get the gist of it. Is that okay? You have that?
It's not necessary that every time at test statistics that you can easily get the exact distribution theory or asymptotic distribution theory. We need that to carry out the inference. So what happens that simple distributions simple statistics which is in the form of linear, like summation xi, summation gxi, etc., are very easy to get the distribution theory. Exact, sometime not exact but asymptotic. But if you have a very complex kind of a statistics, then the distribution theory is very difficult, and that is the time where we actually say that, can computer help us to say something about the distribution? And that is the answer given by Efron, saying that computer gives you the answer in the sense that you can simulate the statistics and try to plot the histogram of that, and simply look at the 95% here and this both sides. That gives you a representation of that confidence interval. Now we can theoretically prove that the bootstrap works. That's the theory part of it, the maths part of it. But an applied part of it is that you use your computer to just simulate that situation. Because distribution is not known, I try to get that distribution by using repeated.
I think our department research scholars are very well versed with this particular phenomena. And you can have a cup of tea with Dr. Pawar for how to go ahead with that, because they have a lot of such statistics whose distribution is completely unknown, but they would like to go ahead and estimate their power. So what they do essentially the same thing.
There is a book by There's a book by Efron on bootstrap, a wonderful, very simple language there. It will be very useful to answer a question. It has permutation tests as well as bootstrap tests on all simple topics. Thank you.
The first question, can there be a non-parametric test is better than a parametric test? You are always surmising that parametric tests are always better than non-parametric test. I'll give you a couple of examples. Probably I do not know whether you are aware of it or you have studied in your master's program. See, take for example sign test. Sign test is the most locally most powerful rank test when the underlying distribution is double exponential. So what does it mean? If you are using x bar to analyze your population median theta in a double exponential, obviously it is going to give a less precise inference about theta as compared to the median, right? In the same way, you know that Wilcoxon's rank test is the locally most powerful test when the underlying distribution is logistic. So what does it mean? It is the same. If you are using a Wilcoxon's rank test, when the underlying distribution is normal, then obviously it will not be good. If you are using mean, it will not be good as compared to the Wilcoxon's rank test when underlying distribution is logistic. So these are two classical examples which clearly opens up the door for non-parametric inference even in the one sample case. So there are so many such tests in two sample and multi-sample case which I do not want to go into, but non-parametric inference, they have been proved to be superior to parametric test under certain conditions when your underlying distribution is not normal. Okay?
You can look at Gibbons and Chakrabarty's book. Actually, or most of the non-parametric books will have a table comparing the efficiency of these non-parametric tests with standard t-test, etc. for location. And then see that for which distribution this efficiency is more. Several books, Gibbons Chakrabarty is there, hundreds and multiple, a couple of books on non-parametric.
So you need to look at the topic on asymptotic efficiency in these books. The books professor has referred, go into that textbook and look at asymptotic efficiency chapter. So that will give you a very clear understanding. Okay. What happens is in the case of non-parametric inference, one of the greatest difficulty that you don't know what is the null distribution or alternative distribution. The distribution under the alternative. Because like Ramanathan said, there are so many candidates to be the alternative distribution, right? Therefore, our comparisons as we do in parametric inference is very, very difficult. That's why researchers came up with this idea of Pitman efficiency. Back in 1942, Pitman came up with this idea, Pitman efficiency. He and with the company of Noether, so they developed this concept which was further contributed by people like Lehman, Hodges and others. So they came up with the idea whenever it is very difficult to evaluate the distribution under H1, how do you compare a parametric test and a non-parametric test? So that is the genesis of the development of Pitman efficiency concept, okay, which is very fundamental to any non-parametric inference or tests.
Yeah. Yes. We can take one or two questions from already listed questions, and the questions are really good questions. There are about 8 questions, but we will not able to reach all of them. What is the role of smoothing in AI ML era. Because some of the questions that already have responded. So whether this AI, like to say something? Please. Fourth question.
Go ahead, then I'll follow it up. You're saying something, right? Or shall I go ahead?
Please go ahead.
Okay. I think I will do is put 2-3 things together here. It is, let me open this one. What is your advice to entry-level research in statistics if he or she wishes to choose inference, the area of research, at the same time role of smoothing in AL/ML data? Okay, both things I can combine, I think. And for that one, I'm going to take a help of some probabilist who actually noted this one some 20 years ago, 21 years ago. And this is what that paper is. You can see the abstract. And he was very, very harsh on statistician. He's called Leo Bryman from Berkeley, a probabilist actually by profession. And he's at statistical modeling. 2 cultures. What 2 cultures is talking about? One is we all talk about. It's a model-based culture. We have model and then we draw the inference. But look at this one, it says. Let me read, that really makes sense. There are 2 cultures in the use of statistical modeling to reach conclusion from data. One assumes that data are generated by a given stochastic model that the other uses algorithmic model and treats the data mechanism as unknown, AI, the machine learning. The statistical community has been committed to the almost exclusively use of data models, that we. This commitment has led to irrelevant theory, questionable conclusions, and has kept statisticians from working on the large range of interesting current problems. Algorithmic modeling, that is both in theory and practice, has developed rapidly in the fields outside statistics. It can be used both on large complex data sets and as a more accurate and informative alternative to data modeling on small data sets. If our goal as a statistician, as a field, is to use data to solve problems, then we need to move away from exclusive dependence on data models and adopt more diverse set of tools. And that is exactly what I was saying earlier. That is, no, we cannot simply stay on the parametric model. You have to think about a lot of non-parametric, machine learning language, everywhere. Okay? So what this author is talking about, he includes, when we say statistician, he includes non-parametric, parametric, or we assume certain things and come to the conclusion. And he's saying, no, that is fine, you do that one, but very often it doesn't, the kind of problems we are facing right now, are much, much different than what we faced before 80s or 90s, when we didn't have kind of the data we get. And therefore, what is the question? Therefore, we must learn to use or incorporate algorithmic models as well. And for algorithmic, smoothing plays a major role. Smoothing, not in the sense of smoothing that has been done until 2000 or 2005, where we have, what he described, assuming there is some density function, some regression function, there is something truth. What we have in statistics, there is something truth, and we estimate. No, that is not the algorithmic modeling is. Algorithmic modeling does not assume something is true, but still the smoothing has a role to play there in pattern recognition, deciding based on half data what the imaginary truth is, and then follow it. Okay. That is what happens. And there is something more I need to add. And if you want to see something of opinion of the homegrown well-known statistician, that is what he said. That is Raju Karandikar. He has said that perhaps in 90% of the problem that needs some decision based on available data, the standard tools in artificial intelligence or machine learning and statistics all combined will yield the best or nearly best answer. Okay. So point is that smoothing has a role to play in those things. Slightly, this answer is slightly general, but it's going to come in some other questions, so I might add that as well here. But he says that but the remaining 10% of the model will need something more than just the tools. And that is some people might ask what the role of statistics then. Well, and this is what is saying. So not all data problems don't have the benefit of big data, and examples are opinion polls, quality control, vaccine identification and approval, drug discovery and approval. These are still, we still play a role. There machine learning has no role to play because there is a finite data set. You go to opinion polls, there is a finite data set. There is not big data. In those cases, there are still problems where statistics is needed, that is sure, but in machine learning and AI, well, those algorithmic ways, there is smoothing, data mining, all other statistics tools has a role to play. And what role to play depends on how good you are in statistics as well as your algorithmic. That is how it will be defined. Some of the programmers of this type that also are where things are not good. Okay, this is what happens. When I say algorithm, AI and machine learning, I call them a data scientist. And this is what we need. A data scientist is a person who is better at statistics than any programmer and better at programming than any statistician. Okay. So again, that also bringing into the answer of my question is, you want to be a statistician as well as programmer. Then you can have both the things together. That means it is a very, very, very essential that we give students both skills, that is statistics as well as coding. Both skills are required, and then we can survive, and that is how we should go further.
Yeah. I think I will just add one statement to that. Yeah, you must know the programming, but programmer may not be knowing statistics. So you are having an added advantage. So if you really pick up some of the programming languages and having given the whole knowledge of statistics, you will be in fact the master of all the situation. Exactly reverse is happening. I would not quote the programmer, means the programs like MBA and so forth. I'm not pointing out to any institute. There they know a bit of statistics and a lot of programming, but they also have a wonderful communication skill, and they dominate the whole statistician class. So it is up to you now to decide whether to pick up good statistics along with the programming, or only go for only statistics, or only go for only programming. Okay? So that is the end of that particular question.
Can I add one?
Yeah, please.
Couple of years before, some of the students did a project with me, and we were trying to see that, for example, there is always, for example, we have ARIMA, we have this time series models, and then at the same time I can use artificial neural network for prediction, LSTM. There are several methods which are part of data science. So what is going to work, for various data sets. So what we found is that in most of the situation, as Professor Prakash Patil was saying, that when you have large data set, naturally you go for algorithmic procedures. Not only that, when you have high non-linearity in the system, what happens that whatever model that you, because your names are, or your tools are restricted. So we know only few, for example, this ARIMA is so straightforward, and you can't really accommodate many things into that. So naturally we need a methodology which works much better. Now at that time I am not seeing that, okay, what is the proof for this one, what is the, can I construct a confidence interval? These are not the questions. I want to do the prediction, and what can give me that. So there are some algorithms which works better. So as you were saying, that situations demand what is better, and accordingly high nonlinearity always win by these data science technologies, methodologies. Whereas if you have much structured data, and if your linearity and other things are available, then your standard methodology works really better. Okay? We found that there are situations where ARIMA is doing much better than some of the data mining techniques. But that is very straight, linear kind of data.
One more comment which personally I was involved in through my relations. My son-in-law works for the company called Discover Credit Card, and he is in the area where he deals with a lot of people who do models here and he checked the models correct or not, etc., etc. The question he asked me following thing. He calls me Dada, what happens? If I put all those things, I get this one, and it says that this person should be given a credit or this person should be a credit. Now that customer comes and asks me that what is the reason that you decline me credit? And I cannot see the model, I cannot understand, could you help me? And then I realized, no, that model is completely algorithmic. What goes in the black spot, what comes out of it is completely unknown. And that means this was developed completely by people who do algorithmic modeling. And that is not a very, that does not put him in a good position or objective position to answer that question. And that is why we need input from there as a statistician. Well, of course we use an algorithmic, but there has to be some statistician doing a bit more to help him to understand the question. So again, same point, we need to have both things together.
Anything you want to add something?
I developed the data science program for my university, and I'll tell you this one. A data science program, we cannot waste these people's mathematical talent. Of course, if they want to, they can come in, and we cannot burden the student who wants to study data science by a lot of mathematics either. So I was told that we are going to have a student who has quantitative ability, which is as good as somebody taken mathematics at 12. That's all his mathematics background is, and we want them to know statistics as well. So this is what how I define the course. In my university, we have STAT 1, STAT 2, which essentially, what is that book called? Inference book, Castle and Berger, or Bickel and Dossum, those kinds of books, those are covered in 2 semesters. Very mathematical, required calculus, required dominated convergence theorem for integration, a background of those things. They don't need to know this, but they need a background of that. We cannot expect this data science student to know this one. So I have devised a course, a 1 semester course called as statistical thinking. In statistical thinking, what things I include? All probability distribution, all test of hypothesis, all inference, basically all inference, confidence interval test, estimation, even your minimum variance and bias estimation, everything covered without using calculus, very much computer based or descriptive way of telling them, understanding whether what is the test, what is the confidence interval. Those could be explained without going too much in detail. So what I'm saying is here is, if you are going to have a spatial data science program where students who do not have a mathematical background like you have to teach slightly differently. That's what I'll say about the statistical theory. But if you have studied a student, you don't want them to become master of statistics by taking the course I just described. They do need to know a bit more mathematical subject.
Can I add something? 2 years before, in fact, I wanted to start a data science program in the department, and we had a meeting with about 10 top people in the country. One from ISI, one from CMI, one from IASC, academicians, and remaining 7 are from industry. They are holding a very senior position in the industry. You know, the feedback that I got is that almost all of them, except one, told that you should have a rigorous training program. Not like what many of these data science schools are giving, like where they just teach the methodology or kind of, black box kind of a thing. This is what and all these people, about 7 of them are leading data scientists in leading, like one is from Citibank and another, almost all of them are top position.
So what I understood from that, they actually, most of them feel that many of the engineers or many of the people who are now becoming data science, their statistics skill is less. I mean, that's what actually we see in the industry. They are good at coding, they come up with things in no time compared to statisticians, but the statistical interpretation skill and the knowledge in depth is less. I'm not joking, this is not my statement, it is almost 7 of them what they told. Of course, academicians always say that we need to go higher level in theory. So there is no question of, I mean, all the, even IASC, I mean, ISI, all these 3 people said that our course should be on the higher side. Of course, there are some technical issues, so we did not even start that. But what I am trying to say that it's like, I think, Kulkarni ma'am, we should not dilute our courses. Because if we dilute, who is going to learn this if we don't teach? In the sense that, I mean, like everybody start teaching it as a methodology. Who will know, I mean, tomorrow, what is the background about a Neyman-Pearson theorem or something like that, whatever it is, dominated convergence theorem, or where it, I mean, like there is, it's slowly becoming, I mean, becoming redundant. And I don't think let other people teach the data science and some jobs may go, but I think they also started realizing that good statisticians are needed. Therefore, I think the demand is still there. That's what my feeling. I mean, I don't know, maybe difference of opinion.
No, but I think there, the statistics should be, even that minimal statistics should be taught by statistical way rather than they learning it themselves. We should teach statistics the way we teach it, but if we need to teach in data science, we should devise a course which is suitable for them rather than somebody else teaching it. That's what I'm saying.
I have a very typical example to give. These people will really appreciate. आपल्याला जर चांगलं गाणं म्हणायचं असेल, चांगला सिंगर व्हायचा असेल, तर सारे गम प जे 7 सूर आहेत त्याला पर्याय नाही आहे. आता आपण कराओकेवर गाणं म्हणायचं का हा विचार करावा. आपला म्हणजे दुर्दैव विलास असा आहे की आपल्याला ते सप्तसूर चांगले आहेत, आपल्याला फक्त रियाज करायचा नाही. तर आपला रियाज कमी पडतो, तेवढा रियाज करा, मग ते सगळं होते. आय थिंक यू अंडरस्टूड व्हॉट आय
सेड. Just to answer Madam's question, I come from an institution where we have 3 undergraduate programs. One is B.Sc Applied Statistics and Analytics, then B.Sc Data Science and B.Sc Artificial Intelligence. I just want to help understand the curriculum of these 3 programs. So in B.Sc Applied Statistics and Analytics, we follow a lot of thrust on core areas in statistics. But as Professor Patil has rightly said, when it comes to data science and AI, we don't have, see for example, concepts are introduced, but we really get into the calculus, especially involving proof of these theorems, lemmas, all those things are not studied, and they are not needed really for who want to make a career at the entry level in industries as a data scientist or maybe AI areas. The one thing that I have learned from my experience by interacting with the people in the industry who are, we have a committee called Program Monitoring Committee, PMC, which consists mainly of industry leaders, especially in the area of statistics and the quantitative techniques. These people, they very openly say they are looking for people with the good skill sets in area of statistics as of now, and they are saying in spite of the advent of artificial intelligence and data science, the industry will keep on looking for people with these skill sets who are core statisticians. Okay, and so they are also fearing that if they recruit people with the data science background, artificial intelligence, down the line the retrenchment will be very fast. There will be a lot of attrition. Because in the real world, a lot of newer and newer concepts keep coming, newer business models keep coming up. So obviously, the industry looks how to get the return by floating those or launching those business models, right? With the kind of knowledge our data science products or AI products have, obviously they feel a lot of pressure how to deliver on these contents. So obviously there will be attrition. So my suggestion is that there is no thinking backward to continue with our curriculum, strong curriculum in the undergraduate program, okay, especially in BSc. So we can't compromise including few papers on AI, ML by taking away mathematics or statistics core topics. So those are the topics which will make anybody stand on their own foot. So that is very important. So this is what I wanted to communicate with respect to these three questions. Yeah. Thank you.
I think we are closing this panel discussion, and we are summing up the whole day. And I take this opportunity to request on behalf of organizing committee to the experts to say a few words about the whole day sessions, maybe in 2 to 3 minutes. Again, that 2-3 minutes limit is as usual, but let us wind up maybe in about 10 minutes so that the further agenda can be taken up. So Professor Ramanathan, please.
Should I go there or here on? Yeah, I think today's deliberations were really useful. In fact, even this panel discussion, they are good, very interesting questions students also asked. I think one thing that you need to learn is that you should also ask questions in the class. Okay, so that can make a lot of changes, because you think that, oh, my question is, so what she was telling, my question may be very simple, everybody knows. Don't think that. If everybody knows, they would not, if they don't know, other people don't know, otherwise they would have asked this question. So most of them don't know actually. That should be the attitude. Don't be, underestimate yourselves. Think that, be bold enough and ask the questions. One thing. And I think about today's proceeding, it was really good. We started with Professor Patil, explaining really some of the symmetry and symmetry related measures and testing and importance of that. And then we had deliberation by Professor Madhav Rao, an application of symmetry and asymmetry, as well as inference procedures in stock marketing, and I also spent some time on non-parametric estimation of regression, or in the context, non-parametric estimation of in the context of dependent data. I think overall it was really good. At least to me, from morning to even to 5:30, you were really attentive. So I'm sure that that may be the case with you. So thanks for being, making me a part of this particular event, and I'm sure that you will also have such kind of good events, very focused and precise kind of things later also. And my request is that students, they should also take part in more better manner, than what you did today. Okay, all the best.
All right, Ramnath spoke very much about the day, so I don't think I need to add anything that one, but I will say following thing. I may not have delivered what you might have expected, but I think you did deliver which I didn't expect. I was very, very impressed with the way things are organized, the kind of quality I see of the homegrown talent. That's excellent. The kind of infrastructure you have, excellent. And what I would like to take it from further up here is possibly more interaction with the people outside, so that our homegrown talent get more chance to think outside the box, outside what other people think. A quick example: I had some interaction with someone, and I learned that they went to LA to check their transport system and all those things. Yes, that's good, but I think we need to go beyond that one. Sorry, my alone thought I'm summarizing, so I might not be summing everything together, but I give one quick example. See, the Western country, I saw following thing. On the campus, it's all nice grass, but sometimes people start walking on somewhere and the grass gets, after walking this sort of, trail forms. What they do, they don't go and block that one. They say, oh, this is how it's evolving. So they put
a pavement there. That's the people to walk and make it nice. So campus, looks nice, doesn't look like something grass is not grown, doesn't look like that. Same way here, I see a lot of problems we have in India, amazing number of problems. We cannot find the solutions only by looking outside and thinking outside. Meaning we have to learn to see how the system is evolving and address those things. Look at the traffic. We have autos, we have motorbikes. You go to Western countries, those are not there. So our roads has to be thought about planning, including those things. And that is possible nowadays with the kind of, machine learning and all those things. We should learn those things, and our brains here could be useful for that. When machine learning, data science, all sorts of projects could be there. I'm just giving an example about the traffic, but there are lots of other problems we could have. And that should help to basic thing what we do research for. We do research to make a world better place to live. And that is our motto essentially. So we should, what I think today happened is that I realize we have resources, we have infrastructure, we have brain power, and now I think we have good leadership as well to direct ourselves to how to world make a better place to live, and it starts with your, home. So university to town to city to state to nation, right? So I think today I think there is, sorry, I might be getting out of my remit, but it was wonderful to interact with you, and I'm very happy to talk to you, and I hope you make use of all those things to expand your knowledge as well as think about the local problems and address those things through this. Okay. Thank you very much. I really enjoyed my stay here.
Just a couple of points. One thing about the wonderful student audience that we have here. I think you have been very patient, and you have stayed all through the morning as well as the evening session, even though we are touching 5 o'clock in the evening, and I can see the enthusiasm and energy in the face of all the youngsters. And obviously this sends a very clear signal to your professors in the department, and also lucky to the Vice Chancellor that your students want more and more such symposium and academic relative activities, so that they can definitely get benefit and craft a very prospective career in their life. The second thing, students, and all of us have given you some glimpse or flavor of non-parametric inference. During the lunch break, some students were talking to me, the mathematics is, we understand the concept, but mathematical part is very difficult, and how do we try to understand that? So nowadays you are all blessed with the easy access to the internet, right? So there are lots of online teaching resources which you can access easily, and you have heard all of us, and I am very sure you would have got some keywords which are part of our presentations. Go home, sit in the comfort of your bedroom or a drawing room or a kitchen, wherever you are comfortable. Take out your smartphone and Google all these keywords and see what they really mean. So that is how you should kickstart the interest in newer and newer topics and research area. That is the one thing. The other thing I always tell wherever I go to my young friends, it is not that you learn only about the topics, but also you need to know the people who came up with those topics and their contribution and life story. That is also very, very important. We have heard about lots of names here, like people like Tipshirani, George Box. These are all great personalities who have contributed tremendously to the development of statistics. I also mentioned about names like Gottfried Noether, E.G.J. Pittman, Eric Lehmann. So these are the the pioneers who actually gave us a kind of employment to be teachers, and also inspiring all of you. So try to get some information about the life and contribution of these statisticians, So in the olden days, we did not have this opportunity. Nowadays, you can simply Google search and their history, entire history is available easily. You will definitely like reading all those charismatic journey and the story about these personalities. I remember, with the permission of Shirke, I will go add 2 more minutes. In those days, if we wanted to know about pioneers from our own country like C.R. Rao or S.N. Roy or maybe Devabrata Basu, so we did not know who they were unless our teachers told us a little thing about that. Until Statistical Publishing Housing Society brought out a very interesting book on life and contribution of great Indian statisticians. So whereas nowadays you have access to all this information. So continue to follow your passion by knowing, passion on statistics by knowing also the personalities who contributed to statistics. Okay. Well, this is what I wanted to share my thoughts as closing remarks. Thank you once again for giving this opportunity.
So no discrimination between panelists and participants. Few of the participants can come forward and say something about the whole day. Yes, please be quick.
Well, very good afternoon. This is, I think, my first visit, official first visit to the department and program after COVID, and this could be the first symposium after COVID. I'm actually a regular visitor to the department, and I have so many objectives because I meet my friends, teachers. This is a different kind of program, so I generally attend so many conference workshops. Conference, you may see there are 7-8 parallel sessions, and in each session there are 7-8 speakers, and there is a lot of diversity, and you don't get many things. But here it is a package. It's one day, only 3 lectures, and same theme. This is nice. So most of this, this is good for master students, because generally we don't see master students in the conference and the research talks, and this is the exposure to the master students, and I saw this number is quite large. And it's very nice. I had my objective that I wanted to listen to Professor Ramanathan on non-parametric time series, and I got some takeaways. So actually, team has worked a lot of, because this logistic. One of the advantages this one-day package is you have less restrictions on logistic also. So I thank the organizers for giving us the opportunity to come here, and thank you one and all.
By the way, I should tell you, he is Dr. Mani Kavle from Savitribai Phule Pune University, and added to that, he is an alumnus of Department of Statistics, Shivaji University.
Good evening all. Dignitaries on the dais, off the dais, and dear participants. It is generally said that mathematics is a static science, whereas statistics is flexible or dynamic science. And therefore we have got more opportunities to deal with real life problems. But because we are stuck in parametric setup, therefore we are losing certain opportunities to deal with real life problems. Because what we are saying is, suppose normal, binomial, chi-square, beta, gamma, these are the distributions that we know, and everything in nature is supposed to follow either of these distributions. So we are fixing certain laws that we only know, and these are the standard laws, and nature should behave in this particular manner. This is our belief. And therefore we are losing out on something, and therefore we should expand our horizon. We should go for the non-parametric setup, and in the morning session, it was frequently said that this is the right time to organize this particular event. I also feel that this is the right time because since post-COVID, we are normalizing our lives, and this is the time when we should non-normalize statistics. Because unless and until we non-normalize statistics, we will lose out certain opportunities and computer scientists will go ahead. And therefore, I really congratulate Department of Statistics for choosing this particular theme. The entire arrangement, right from the registration process to the accommodation, breakfast, lunch, all these arrangements were literally at par, and therefore I congratulate on behalf of all the participants to the Department of Statistics. Thank you all.
Thank you so much for your responses and summarizing the whole day of the conference. I must congratulate Professor Mahadik and his team for an excellent academic event organized today. And at the same time, I must appreciate the whole day presence of all the three experts, Professor Prakash Patil, Professor Madhav Rao, and Professor Ramanathan. What is the takeaway from this particular? So, I'm not an expert saying that the whole day what has happened and what you should do. But I would simply say, see this, every day we learn something and it gets accumulated. And in our familiar language, we learn epsilon today. And we will put that epsilon with us. And interestingly, our epsilon is always positive. So you have got something positive today, and you will keep that positive all the while with you. Keep on adding every day that positive, and you will get a big positive. With this, and whatever comments and suggestions have been made by the experts, particularly knowing what we do not know, doing what we do not do, and interacting with experts as and when it is possible. I think if you keep that practice, I think life will be comfortable. Professor Prasad, the founder, professor and HOD of this department, used to say, and that I'm just passing this to the students, of course. He used to say that in the first lecture itself, he used to say that, see, if you enjoy these 2 years, you will have to suffer the whole life. And if you really do something good, you need to enjoy the whole life. So it is up to you whether to enjoy the 2 years and do nothing, or you do everything for the 2 years and then enjoy the whole life. With this, I wish the very best, every success. Thank you.
So, I am here to propose a vote of thanks, last part of this particular symposium. First of all, we would like to thank authorities of Shivaji University, Kolhapur for providing financial assistance to organize this particular program on the occasion of Diamond Jubilee year of Shivaji University, Kolhapur. I would like to thank Honorable Vice Chancellor, Professor D.T. Shirke, for encouraging us to organize this particular symposium and for helping us or for helping this activity in all the ways, right from financial support to getting this hall and presiding over the inaugural session and chairing this particular panel session. Thank you, sir. I am, on behalf of organizing committee, I am thankful to all the 3 speakers for sparing their valuable time for traveling along the way for delivering a lecture. So thank you, Patil sir, Professor K.S. Madhavrao sir and T.V. Ramanathan sir. I also wish to express my gratitude to Professor S.B. Mahadik, head of the department, for his time to time guidance for the organization of this particular symposium and encouraging each and every student and research scholars to attend this and to participate in this. Friends, as you know, event like this cannot happen overnight. It needs preparation, and the wheels will start rolling few weeks ago, and I am very fortunate to be backed by a very motivating team of my colleagues, Professor Dr. H.V. Kulkarni, S.V. Rajguru, Adjunct Professor Sanjay Ganjwe, Assistant Professor Sachin Patil, Dr. Santosh Sutar, S.V. Rajguru, and our research scholars, especially Mr. Devre, Ms. Shivali Suryavanshi, Amarjit, and all our M.Sc Part 1 and Part 2 students for their help in the organization of this particular event. And lastly, I am thankful to all the participants for giving an encouraging response to this particular event. I thank the PRO and this committee for these fellows for live streaming. I thank one in all. Thank you very much. And with this, I declare that this symposium is over.
Participants, your certificates are ready. You can collect it from the registration desk outside. Yes. विद्यार्थ्यांनी नंतर घ्यायचेत आपले MSc 1 आणि MSc 2 फक्त पार्टिसिपंट